handshake, let me say in the traditional Konkani way, which is our local language. I extend Sagrang Hao Maja Maya Mugatsa Yog Kar Deta. This is a very important event for us in the college. Again, there are highly eminent academicians and researchers who have joined this online symposium on material science and innovation for a sustainable society. I also express the hope that all of you are safe, and let me say in the traditional Konkani way, which is our local language. Challenging times for all of us. They say that there is, this is a very important event for any adversary and challenge. Again, there are highly eminent academicians and researchers who have joined this online symposium. Also take this opportunity on material science and innovation. The initiative taken by our principal. I also express the hope that to organize this online, let me say, join the traditional Konkani way, very local language. I'm happy to note this is a very important event for any adversary and challenge. Major university. There are highly eminent academicians. Dr. Borkar can refresh my memory. Join this online and also take this opportunity on material science and innovation. The initiative taken by our sometime this last year during the same time to organize this vice chancellor was joined the traditional Konkani ceremony. And I'm glad to note that this sort of collaboration is continuing, and now through this symposium, which hopefully will set a new benchmark in academic collaboration. We are indeed very grateful to Professor Takahiro Muruyama of Nanoscience Research Center at Major University, who has taken specific interest and has given all his guidance and support in this specific collaboration. I am also glad to note that this symposium is co-hosted with Government College Khandola under the cluster of colleges in Goa for research in chemistry. This is something that has been started recently, this cluster approach, and I must thank the Honorable Vice Chancellor for providing the leadership. You know, we have discussed, I have been fortunate enough to be a part of the Executive Council with the Honorable Vice Chancellor, and I really approach his, the initiative that it takes, that together we are one, and I think the cluster approach is basically in the true spirit of sharing knowledge for the larger public good. I can't express my feelings, but just be very, very thankful to the rare privilege to have a Nobel laureate to deliver the keynote address. And it's such an honor with the participation of Professor Akira Yoshino, son of Major University, the 2019 Nobel laureate in chemistry. On behalf of all of us present at the symposium, my very warm welcome to Professor Akira Yoshino and to Professor Takahiro Maruyama of Major University, Japan. I am happy to have our Honorable Vice Chancellor, Professor Varun Sahani, who's always been very, very supportive. He's has always been talking about meaningful research to be carried out in colleges under his university. And I'm glad that our own college is following that advice and going ahead in the right direction. I also note and acknowledge the presence of Professor Vittal Tilvi, who represents the Directorate of Higher Education, another body who has always believed in collaborative approach, and all the eminent resource persons and researchers from Goa, other regions of India, and also overseas. All of us have witnessed during the last 6 months the pandemic that has hampered people-to-people contact across the globe. But it has not failed to dampen the human spirit of learning, sharing, and collaboration. I just hope the outcome of this seminar, I'm not a person from this field, and as a common man and as somebody from a business field, I hope that material science, basically the design process, the operational efficiency process, ultimately contributes to an enriched human life. We are all struggling here. And I think COVID-19 also is a side effect of many things that are happening to the environment. And one ray of hope is that if we do sustainable and systematic research in material sciences, we could get rid of many of the environmental hazards that we are facing. With this, I sign off by wishing the symposium every success for the next 2 days. Thank you.
Thank you very much, sir, for your constant support as well as your words. May I now invite the guest of honor, Professor Vittal Tilvi, an Indian-American astronomer, the founder of the farthest group of galaxies. Joining us today is the representative of the Directorate of Higher Education to kindly address the participants.
A very good morning and konnichiwa to my Japanese friends. Professor Varun Sahani, Vice Chancellor of Goa University, Professor Yoshino, the Nobel Prize recipient 2019, Sri Dhempe, my colleagues, friends, and young researchers. It is indeed a pleasure to be part of this international symposium on material science and sustainability. And moreover, it is my privilege to be listening to the world experts and especially the wisdom that we will get from Professor Yoshino. 7 years ago, I had an opportunity to work with one other Nobel Prize recipient in astronomy and for discovering the accelerated expansion of the universe. So he had discovered that universe is not just expanding, but it is expanding at even a faster rate. So it was called the accelerated expansion of the universe. And I had that privilege not simply because of the technical knowledge I gained, but what I learned is he had a completely different approach at looking problems. So it was a completely different way, not just research problems, but in general, looking at life. And I still remember one of the stories he had told during our first conversation. And the story goes like this. And this story had high impact on my career since then, in my research since then. And so the story goes like this. This is a real story. Until April 1954, so there was something called this 4-minute a mile barrier. That means until 1954, no human could run 1 mile in less than 4 minutes. So this is a 4-minute a mile barrier. And so several athletes had tried this for centuries until one day in May 1954, when a young junior doctor, not even a professional athlete, but a young junior doctor broke this barrier. And do you know what happened since then until now? More than 1,400 times this record has been broken. So what it means is that until April 1954, people had accepted that there was some physical limit, a human limitation to break this barrier, 4-minute a mile barrier. But once this barrier was broken, on an average, every month this record was broken almost 2 times a month. So essentially, once we realize that, once we can break a barrier, that field will grow exponentially. And something similar has happened recently. Early 2020, me and my team discovered what we later found out was the most distant group of galaxy in the universe. And this discovery is supposed to be done by using the space telescopes that are yet to be launched. But we thought that we could still use the existing facilities, the existing telescopes on the ground, on the planet, and we could discover. And so eventually we made this world record in early 2020 for discovering the most distant group of galaxy in the universe. And I think something similar is happening in material science, especially the nanoscience and advent of nanotechnology. So what we used to think about the bulk material, we had to use a lot of material to make material stronger, material that are very, very long. But with the advent of nanomaterials, we can make the same material as the strongest material and at the same time the lightest material. And that is possible only because of the nanomaterials, nanoscience. And I think this field, especially to the young researcher, this field is open, and you are on the track where you can break this barrier, because I believe that nanoscience, nanotechnology will go in every corner of our life, because people have demonstrated that now we can use the nanomaterials to target drug delivery, for water purification, for energy use, and I hope that this symposium will bring a lot of researchers around the world for furthering the progress in this specific discipline. Thank you.
Thank you very much, Professor Tilvi, for your perceptive insights into the research of this kind and stature. We will now release the abstract book. The abstract book consists of abstracts of all the invited lectures and oral presentations that will be carried out as part of the proceedings of this symposium. Dear participants, you must have received a copy of the abstract book as an email on your registered IDs. Dear participants, this is the abstract book of the International Symposium on Material Science. The abstract book, which you may have already received on your registered IDs. We are extremely honored today to have with us Honorable Vice Chancellor of Goa University, Professor Varun Sahni, a Professor of International Politics at the Center for International Politics, Organization and Disarmament, New Delhi, India. Professor Sahni has also been the Vice Chancellor of the University of Jammu, India from 2008 to 2012. He has been Junior Research Fellow and Junior Dean at Lincoln College, Oxford. He has been felicitated with prestigious honors such as V.K.R.V. Rao Prize in Social Sciences by Indian Council of Social Science Research and Personnalité d'Avenir by the French Foreign Ministry. This is only to name a few. With his belief that universities are built over time, lecture by lecture, experiment by experiment, where the engine room is in the teaching department, today, as the Vice Chancellor of Goa University, he has been guiding institutions towards holistic advancement and excellence. I request Professor Varun Sahni to kindly address this virtual gathering.
Mr. Srinivas Dhempe, all our distinguished resource persons from Japan, Portugal, and India, Professor Vittal Tilvi, Principal Vrinda Borkar, Principal Purnakala Samant, and all the other distinguished principals from the colleges associated with the cluster of colleges for research in chemistry, Goa, faculty colleagues, student friends, ladies and gentlemen, a very good morning to all of you, and welcome to this International Symposium on Material Science for Innovation for Sustainable Society, organized in these very, very difficult times. I would like, on behalf of Goa University, to extend a very warm welcome to all of our distinguished resource persons, Professor Akira Yoshino, my brother Vice Chancellor Professor R.K. Verma, Professor Shunji Bando, Dr. Nirmala Ballav, Professor Sagar Mitra, Professor N.B. Singh, Professor Meenal Kaushik, Professor K.S. Rane, Dr. Kamal Sharma, Professor Narendranath Ghosh, and Professor Jose Luis Figueiredo. Thank you so much, distinguished colleagues, for joining us in this two-day exercise, where we will hopefully explore some of the very important frontiers that are emerging in materials science. And I hope that this will be, in every sense, an enlightening international symposium for all participants. I would like to congratulate Principal Vrinda Borkar and all of her fellow principals associated with the cluster of colleges for research in chemistry, Goa. I think it's wonderful that you have taken the effort to organize an international symposium of this quality in circumstances that we all recognize are extremely arduous and difficult. We are, of course, deeply honored that the keynote address will be delivered by Professor Akira Yoshino from Major University. I mean, he, of course, is one of the iconic names in science of our times. His work, his path-breaking research, which has been the basis for the creation of the first safe production-viable lithium-ion battery, is something that we are all familiar with. It touches our lives on a daily basis. And of course, he is the Nobel laureate in chemistry for the year 2019. His work has led directly to all the devices that we are using for this very interaction across the continents, spanning Japan, Portugal, and India. It would not have been possible without the technological bedrock of his research upon which our global information age has been constructed. So we are in the presence of greatness with him and our other distinguished resource persons. And I'm sure that, this would be hugely inspiring, particularly for our students and for our young researchers. We at Goa University are really trying to take significant steps to strengthen material science research and teaching. We are in the process of setting up a materials characterization laboratory. A lot of materials research is already being done in our School of Chemical Sciences and in our Department of Physics and Department of Electronics. But we have now decided, first of all, to merge our departments of Physics, Electronics, and Mathematics to create a School of Physical and Applied Sciences. But over and above that, we are setting up this materials characterization laboratory as a central facility for all researchers, faculty, and students alike who are working in the area of the material sciences. And we hope once this facility is set up, that it will be a facility that can be used by our collegiate system as well. I wish the International Symposium a grand success. I hope that all the delegates and participants really have an enriching and enlightening experience. I shared the sentiments of Mr. Srinivas Dhempe. We love in Goa to have colleagues and friends come and visit us. Goa is a really, really beautiful part of the world. And, we would have loved to have given you our traditional hospitality. But please understand that, we are doing precisely that in a virtual sense. I really hope that this international symposium would stimulate further innovations in the very important fields pertaining to material science. So once again, thank you very much for inviting me to be a part of these proceedings. And I wish all of you a very, very wonderful 2 fruitful days ahead. Thank you.
Thank you very much, Sir Professor Varun Sahni, Honorable Vice Chancellor of Goa University, for your words on this occasion. May I now invite Professor Purnakala Samant, Principal of Government College Khandola, to propose the vote of thanks.
A very good morning to all the respected dignitaries, colleagues, young research scholars, and participants from various places in India and abroad. I deem it a great honor and privilege to propose vote of thanks on this memorable occasion. My words of gratitude towards Nobel laureate Professor Akira Yoshino, Meiji University, Japan, for accepting our invitation to deliver the keynote address, which will charge the minds of young scientists in the area of lithium-ion batteries. Professor Yoshino, we all look upon you as a role model. On behalf of organizing committee and all the webinar participants, I once again convey our thanks to Professor Akira Yoshino. My special thanks to academicians from Nanomaterials Research Center, Meiji University, Japan, for collaborating this international symposium with Dhempe College of Arts and Science, Miramar, Goa, along with cluster of colleges for Research Center in Chemistry, Goa. I am thankful to our chief guest, Professor Varun Sahani, Vice Chancellor, Goa University, for taking time off from his busy schedule and gracing the occasion. Professor Sahani, being a strong academician, always guide, help and encourages the growth of affiliated colleges towards perfection. Thank you, Professor Varun Sahani, for your presence. I am grateful to the chairman of Dhempe Charities Trust, Srinivas Dhempe, for gracing this occasion in spite of his busy schedule. Under the guidance and leadership of Dhempe College has achieved many milestones in the educational sector, and today it's one such event. Thank you, Sri Srinivas Dhempe. My special thanks to Sri Prasad Lolekar, Director, Directorate of Higher Education, for his constant motivation to conduct such educational related activities. My thanks are due to the guest of honor, Dr. Vittal Tilvi, Professor, Research Development and Innovation, Directorate of Higher Education, for your esteemed presence. My special thanks to the leader of organizing team, Professor and Principal Vrunda Borkar, a visionary lady, a lighthouse of knowledge, with a perfect blend of discipline and punctuality. Compare Ms. Akshata and all her team members from Department of Chemistry, Dhempe College, Miramar, who worked tirelessly with meticulous planning in short time in holding this 2-day webinar on International Symposium on Material Science and Innovation for Sustainability Society, a great success. I am thankful to all the invited speakers for accepting our invitation and adding glory to this event. Our thanks also goes to the print and digital media for publicity. I wish you all successful and fruitful deliberation. Thank you, one and all.
Thank you, Madam. May I now invite Professor K.S. Rani, former professor of Goa University, to take over the next session, a particularly important session that we all have been looking forward to, the keynote address by Professor Akira Yoshino. Over to Professor K.S. Rani.
Good morning. Can you hear me?
Oh, yes.
Yeah. Good morning to everybody. I thank the organizers to giving me this opportunity to chair this important session. I welcome one and all, especially Nobel laureate Professor Akira Yoshino, for having accepted our invitation and gracing this conference. To begin with, I call upon Professor Dr. Vrunda Borkar, Principal, Dhempe College of Arts and Science, Miramar, Goa. Dr. Vrunda is a teacher, administrator, and above all, she is a researcher and the convener of this conference. I request Dr. Vrunda to introduce our keynote addressee, Nobel laureate Akira Yoshino. Please.
Thank you, Sir Rane. We all are honored by presence of Professor Akira Yoshino, distinguished professor of Mejo University. It is a challenging task, sir, for me to narrate a long journey of innovation and research in few minutes. A journey that clearly exemplifies that innovation and research should be oriented towards social benefit, and the byproduct of research should lead to a degree. Professor Yoshino completed BS and MS degrees from Kyoto University and joined Asahi Kasei Corporation in 1972. He worked in battery recharge group. After 1980, the need was felt for small, lightweight, rechargeable batteries for mobile, laptop, and video cameras. The conventional rechargeable batteries, such as lead-acid batteries, nickel-cadmium batteries, had limitations to reduction in the size and weight. We wanted to put the mobiles in the pocket. So he focused on the creation of non-aqueous electrolyte secondary batteries to meet the emerging need. He conceived the lithium-ion battery and the work was patented in 1985. The prototype was fabricated in 1986. He worked as manager, product development, then technical development, and in 1997 as manager, rechargeable ion battery group at Asahi Corporation. Later worked on development of peripheral technology such as safety device technology, which was very important to make any device portable. His work received appreciation from Chemical Society of Japan by awarding Chemical Technology Prize in 1999, Battery Division Technology Award from Electrochemical Society, and Ichimura Prize for development and commercialization of lithium-ion battery. In 2003, after receiving the fellowship from corporation, he completed his doctorate in 2005 from prestigious Osaka University. He became general manager of Yoshino laboratory in Asahi Corporation and in 2011, president of Lithium-Ion Battery Technology Evaluation Center. He was designated as Fellow of Chemical Society of Japan and won Medal for Environmental and Safety Technologies from Institute of Electrical and Electronic Engineers for developing the battery, which enables significant fuel conservation and reduced emission as power storage for electrical vehicles. He was recipient of Global Energy Prize, Cato Memorial Prize, Charles Clark Draper Prize for Engineering from National Academy of Engineering, followed by National Institute of Material Science Award. He joined as professor in Meiji University in 2017 and also at Kyushu University. He received Japan Prize and European Inventor Award in November 2019, the Order of Culture, Person of Cultural Merit. A long journey of innovations culminated in a prestigious Nobel Prize in Chemistry in December 2019. I welcome Nobel laureate Professor Akira Yoshino to address the virtual gathering. His keynote address will definitely inspire and motivate the young minds in India. Welcome you, sir.
Thank you.
Thank you very much, Vrinda. I now call upon Professor Akira Yoshino to address our graduate, postgraduate, research students, and also researchers. Professor Akira, kindly note that soon after your address, we'll take up some 5 or 6 questions from the students only, not a senior person. We'll take the questions from the students community, not from the researchers. And you can answer those things for them and kindly address the gathering. Hello?
Hello.
Yeah.
This is Akira speaking.
Yeah.
Hello.
Yeah.
Okay, would you open my present PowerPoint file? And here, this is a photo of research laboratory members at Kyoto University. And in 1972, I joined Asahi Kasei Corporation. And next one is marriage. 1974. Wonderful woman. Nice, Miko-san. And in 1981, I started the basic research on new secondary battery systems. Okay, next please. I move to the next topics, brief history of the lithium-ion battery. Next, please. This is the definition of the lithium-ion battery, and also in this slide, how each of laureate fit in. I read the definition of the lithium-ion battery. A non-aqueous rechargeable battery operating on the principle of electrochemical intercalation is one point. And having a metal oxide containing lithium ions as cathode. This is the second point. And third point is negative electrode, carbonaceous material as anode. So in 1976, Professor Whittingham, also he is a laureate of Nobel Prize in Chemistry last year. He proposed a new theory. First one, electrochemical intercalation. World first, Professor Whittingham proposed this electrochemical intercalation theory. It is his contribution to Nobel Prize. And in 1980, Professor Good Enough, he discovered new cathode material. This new cathode material is metal oxide containing lithium ion. Containing lithium ion is very, very important word. So, and Akira Yoshino, discovered new anode material, carbonaceous material, and combined with new cathode material discovered by Good Enough, and made a basic principle of current lithium-ion battery. Okay, next, please. This is very, very important slide, I think. This slide shows the rules of lithium-ion battery technology. Yeah, there are 3 Nobel Prize in this lithium-ion battery technology. First one is 1981. 1981. Professor Fukui and Hoffman proposed a new frontier orbital theory. By this achievement, Professor Fukui and Hoffman received Nobel Prize in Chemistry in 1981. I think this is the roots of lithium-ion battery technology. And in 2000, Professor Higa and McDermid and Shirakawa received Nobel Prize in Chemistry in 2000. Their achievement is the discovery of electroconductive polymers. It is called polyacetylene. This is very, very functional compound. And this polyacetylene will be predicted by frontier orbital theory. By frontier orbital theory, if someone prepare polyacetylene will be electroconductive. This is prediction by frontier orbital theory. Also, the appearance of polyacetylene, it looks like metal. It's very shiny surface, like aluminum foil or nickel foil. So then Higa and McDermid, Shirakawa discovered this new polymer materials and proved that this polyacetylene is electroconductivity, and the surface very, very shiny, like metal surface. Okay. Then last year, 2019, Professor Whittingham and Goodenough and I, Akira Yoshino, received Nobel Prize by the invention of lithium-ion batteries. These three Nobel Prize is very closely related because the initial start of my research was this polyacetylene. I started basic research from 1981 about this polyacetylene. This is the start of my research. Okay. Next slide, please. This is the polyacetylene. Polyacetylene is prepared by the polymerization of acetylene gas, and the chemical structure is shown here, polyacetylene. It looks like this is this photo is a sample of polyacetylene. It looks like metallic foil, but this is a plastic film, very, very curious, unique materials. So I'm very interested in this polyacetylene and start basic research from 1981. And this polyacetylene has many, many functions, electric conductivity. Also, this polyacetylene has electrochemical functions. So it means this polyacetylene is one candidate for battery materials. So next page, please. Okay. I researched the situation of the battery industry at that time and found that many researchers were trying to make a new rechargeable battery that would be small and dry. But it was very, very difficult to commercialize. So this difficulty caused from anode materials. So I found that a new anode material was needed. So I decided to try to using the polyacetylene as anode material. This is a start of this lithium-ion battery research. And I did many experiments and found that we store a lot of electricity. It can be it's possible to store a lot of electricity, and its performance was very stable even after many charge and recycling process. So next step is selection of cathode materials. Okay, I needed the most suitable cathode material to be combined with polyacetylene anode. Next page, please. This table shows the cathode material which was proposed at that time. There are many kinds of cathode material was proposed for secondary battery. in this table shows the example of cathode material. No, you can see these all cathode material does not contain lithium cation. Okay, it means very, very important. In this, in case of metallic lithium anode, metal lithium anode material, there are no problems to make battery systems, because in this equations, lithium means lithium metal. Of course, the lithium cation is required to charge and discharging process. In case of metallic lithium cations provided by automatically from metallic lithium anode. So there's no problems. But in case of polyacid anode, PA means polyacetylene. Polyacetylene does not contain lithium cation. Also, this titanium disulfide does not contain lithium cation. So it is impossible to make battery systems, because both anode material and cathode material does not contain lithium cation. So it is impossible to make battery. Next page, please. Almost same time, Professor Goodenough, he discovered new cathode material. He discovered lithium cobalt oxide, new cathode material. This is the world first record of cathode material which contains lithium cation. I wanted to this compound, so I prepared this lithium cobalt oxide and combined with polyacetylene anode. Then it became possible to make new secondary battery systems. Next, please. By this equation, the PA means polyacetylene and lithium cobalt oxide. By combination of these two compounds, it became possible to charge and discharge. This is the origin of the present lithium-ion battery. Anode material was PA, polyacetylene. The cathode material is lithium cobalt oxide. I invented in this new battery system in 1983. Okay. Next page, please. Please click twice. One more. Okay, thank you. Then I invented a new battery system and make a second battery. But unfortunately, the purpose of this research is light and small secondary battery. But unfortunately, this new battery system was based on weight. It is almost weight of a battery almost 1/3 compared with the nickel cadmium secondary battery. It's okay, but based on volume, almost same with nickel cadmium. And I made this sample to some customers, which is important. Lightweight or small volume. All customer reply from all customer was all they said small. Small is the most important. The volume is very most important. It was their answer. So I think from polyacetylene to other and carbon. I estimated many other materials such as carbonaceous material, which was available in those days. But unfortunately, this new does not show the good performance. But I obtained some new carbonaceous material. New carbonaceous material is VGCF, vapor phase grown carbon fiber. It's a new carbon fibers. I obtained this sample from acetic fiber and this center. Another researcher researched this VGCF. So I got this sample of VGCF and estimated the performance. It was very better performance. So I changed anode materials from polyacetylene to carbonaceous materials. Okay. By this replacing new battery system becomes lightweight and also small. Okay. Next slide, please. This is the C means carbonaceous materials. In this equation, the charge and discharge becomes possible. This is the current basic concept combination of current lithium-ion batteries. I invented it in 1985. So I moved to next step, development stage. Okay. Next slide, please. I say the commercialization of new secondary battery system using a non-aqueous electrolyte system. It was very difficult to commercialize. The reason was quick please. Please click. Okay, thank you. The fatal issues caused from metallic lithium negative. And also these issues cause the safety problems. Click again, please. So I should to prove this new battery system overcame this safety problems. It was very important. Next slide, please. So I prepared the lithium-ion battery for this safety test. and carried out world's first safety test of lithium-ion battery in 1986. I want to show the scene of this experiment by video file. This slide is a test method. Iron block dropped on the batteries and crashed. And what happened? This is a safety test, very, very simple safety test. And this slide is a sample is a battery using metallic lithium as anode. This is a primary battery, primary. And right photo is a prototype lithium-ion batteries. So I want to show. Next slide, please. First, battery using metallic lithium. Okay, click again, please. Fire. So, in case of metallic lithium anode, it's called fire. It's a safety issue. Okay. Thank you. Next video file, please. Middle one, yeah, thank you. I am going to drop down to the surface of the battery, and battery was crushed. If in this safety test, this battery is called fire, I believe it was impossible to commercialize lithium-ion battery. So I believe that this safety test was very, very important for me. Also, I believe this is a moment when the lithium-ion battery was born, I believe. Thank you. Please back to the PowerPoint files. I want to move to the next topics, future. I received a Nobel Prize in Chemistry last year. The reason for this award, there were two reasons. The first reason, one is lithium-ion battery made the mobile IT society possible. Mobile IT society was created by lithium-ion battery. This is one reason. The second reason is shown here, sustainable society. The lithium battery is expected to contribute to sustainable society. This is the reason for Nobel Prize in chemistry last year. Okay, next page, please. Okay, next page, please. Okay. Okay, so now I want to talk about the future. In this battlefield, it's very, very aggressive, and this slide shows the capacity base of market scale of lithium batteries. Golden bar shows the application for mobile IT. The red bar shows the application for vehicle, electronic vehicle. And in 2010, almost 100% was only for mobile IT. Now, application for electric vehicle is increasing rapidly. And in 2081, application for EV exceeded mobile IT application. Next page, please. This is the market forecast to 2025. Application for electric vehicle increased rapidly. This was is predicted. But unfortunately, in 2025, the ratio of vehicle, the ratio of electric vehicle is only 15%. Very, very small ratio, even if in 2025. So it is very important. What happens after 2025? It is very important point. So this market forecast is related to with the creation of a sustainable society. Okay. Okay. Next page, please. People have talked a lot about environment problems, and we still don't really have an answer, no answer even up to now. We continue to have a dilemma between the environment, economy, and convenience. Priority is only convenience. Please, next slide, please. It becomes this way. Next slide, please. If only convenient, if only environment, it becomes this way. So, is there a way out of this dilemma? It is very, very important. Is it possible? Yes, it is possible, I believe. Okay, I want to show the example of a future society. Next slide, please. This is there are many arguments about future car society. There are many buzzwords to predict the future automobile societies. Most important buzzword is CASE, C-A-S-E. C means connected, all automobiles connected by internet. A means autonomous, by AI technology. S means shared, and E means electric. This is a very important buzzword to predict the future car society. Finally, I want to show the future society around by video files around 6 minutes. Yes, please.
High-performance rechargeable batteries, electric vehicles, artificial intelligence, the Internet of Things. A combination of these technologies will soon bring about a radical upheaval that goes beyond what we can imagine today. Energy is changing. The ET revolution will reshape the world. We face challenges of resources, the environment, and energy. Innovative technology is arising for the environment and energy. The ET revolution. Leading the way in the ET revolution that will impact the whole of society is the automobile. By understanding the evolution of the automobile, we can see the complete picture of the ET revolution. What changes will this revolution actually make in society? In 2030, people's lives are centered on the AIEV here in a metropolis shaped by the ET revolution. Everywhere you look, there are AIEVs, autonomous vehicles driven by artificial intelligence. When you want to go somewhere, you call one like a taxi, and the nearest AIEV comes to pick you up.
Good morning, Akira. It seems you were late last night. How do you feel?
I didn't get enough sleep. I feel a little sluggish.
The fresh juice stand everybody's talking about is nearby. How about a rejuvenating beverage?
Say, that would be a nice topic of conversation at the office. So fresh kiwi is the most popular. Okay, I'll have that.
You want this one?
Please. AIEVs directly connect users with establishments and services, such as restaurants, cinemas, and hospitals, playing a vital role as a hub of the economy. Inside the autonomous vehicle, AI provides various services including language study, fitness, and shopping, tailored to the user. In a society where all the vehicles are autonomous, there are no accidents or traffic jams. After dropping the user off at the destination, the AIEV goes to a charging station or to pick up another user. Such AIEV services are provided for a monthly fee, like a smartphone. Users choose the provider and plan that suits their own needs. Rather than cars owned by each person, there are AIEVs shared by everyone. This reduces the cost for each person to 1/7. This new kind of transportation is available not only in big cities, but also in rural areas. With shared AIEVs, there is a new social structure with extremely little environmental burden. In addition to carrying people around, AIEVs play the role of carrying energy to places that need it. AIEVs spread throughout the whole society store enough electricity to last for 10 hours if 50 power plants shut down. Charging and discharging are simple. Fully automated recharging and discharging stations are everywhere. When the power supply is stable, the AIEVs all charge up. When power is in short supply, they discharge wherever needed. Together, they function as a giant reservoir of energy that is drained and refilled. This function serves to overcome the fluctuation of renewable energy supply. Dispersed throughout society, AIEVs form the infrastructure that allows power to be bought and sold, which has a huge economic benefit. Sharing things with minimum use of resources, using energy efficiently, reducing the supply volume. This is not only friendly to the environment, but also reduces costs. The social transformation of the ET revolution extends beyond AIEVs. The ET revolution lets people live in comfort effortlessly, without restraint or frugality. This era is coming.
Thank you.
Where?
Please return to PowerPoint file. Okay. Final. Okay. I exceeded my presentation time, so the next page, please. Thank you very much for your attention. I'm very sorry to exceed my presentation time. Thank you.
Hello.
Hello.
You can go ahead for 5 minutes more if you want to finish off everything. You want to continue some time?
Pardon me.
Are you finished? Hello.
Hello.
Professor, are you finished?
Yes.
Hello.
Professor Rane, he has completed his presentation. So he's waiting for the listings. Yeah.
Has he finished it? Hello.
Hello.
Hello, Professor. Can you hear me? Hello. Can you hear me, Professor?
Actually, we can hear you, sir.
Yeah. He is not able to hear.
So you start asking, then perhaps he may respond.
Okay. Okay. No, he should know what I am asking you. Hello. I think connection is gone or something. Is somebody is monitoring that one?
Professor Yoshino,
Yes.
shall we start with the question session?
Yeah.
Yeah.
Okay. Okay. Hello, Professor. There are 5 questions I have chosen. There are many people who have asked many questions, but I have chosen only 5 questions. The first question comes from Shubhda Naik from Dhempe College, Goa. The question is, could ultra capacitors replace batteries in future electric vehicles?
Mm-hmm.
Could ultra capacitors replace batteries in future in electric vehicles?
Mm-hmm. Okay, I can't hear very well because it's so noisy. Would you,
Okay, I'll slowly ask you. Could ultra capacitors replace batteries in future in electric vehicles?
Mm-hmm.
There is a question asked by a student.
Sorry, I can't hear the.
Okay.
So noisy.
Noise is there. Okay. Could ultra capacitors replace batteries in future electric vehicles? Okay, I'll pose the second question at least. Why iron oxide is not used instead of cobalt oxide, which is being environmentally unfriendly?
Yeah.
Why iron oxide is not used instead of cobalt oxide, when the cobalt oxide is being environmentally unfriendly?
Yeah. Do you ask about the natural source of cobalt?
No, not natural source. Why we use? Why people are using cobalt oxide, which is environmentally not that friendly? Can we use iron oxide?
Yeah.
That is a question asked by Gautami.
I think that's a way to change the cobalt to
iron
other metals such as nickel.
Okay. The third question comes: which special property of carbonaceous material motivated Professor Akira to choose as an anode material? Which special property of a carbonaceous material motivated Professor Akira to choose as an anode material? Which special property?
Yeah.
I shall again repeat it. Which special property of a carbonaceous material motivated Professor Akira to choose as an anode material? Which special property that made you to use as an anode material? Which special property of that?
Okay, so I'm very, very sorry. I can't hear clearly.
Okay. No problem.
I'm very sorry.
We'll pose it.
Sir,
No, it's
sir,
okay,
one
no
sec.
problem.
Sir, one sec.
No problem.
If you
We'll
can see the chat box, we have put 2 questions there. Okay. So in the chat box also there are questions. He can give the answers after some time. No issue.
True. That's what we say. Only I wanted to say that these are the students who pose the questions. At least the students should feel happy. You understand? So, as you said rightly, that questions can be posed to him, and in due course of time, he can answer to those questions. You understand my point, Dr. Varunda?
Yeah. Yes.
That way, at least the last question is also a very nice one. Most of the non-aqueous batteries are prone to fire hazards. This is a question at least the other audience will understand. So probably you are not able to catch it. Most of the non-aqueous batteries are prone to fire hazards.
Professor Maruyama.
Yeah. Okay. No problem, Professor. Now you can answer them in the due course of time. Only I wanted to tell that how the questions have been coined by our own students. That was my point of this one too.
最後のはよく聞こえなかったんですけど、
Anyway, okay. Vanda, shall I close this session by thanking Professor? Vanda.
Yeah. Yes, sir.
Yeah. Okay. Thank you very much, Professor, for your enlightened talk. And I think it's most nicely explained by you in a very systematic manner, the way that your journey went through all these almost 40-50 years. It is it is really unimaginable for us from a Nobel laureate telling of his history of the battery. So we are really encouraged by your this talk, and I think it will go in a long way. Our students will emulate your ideas and your enthusiasm. And I thank you for taking some time, and nothing, no issue about this one. We are very happy to have you here, and we'll try to send all the questions, whatever the students are posed to us, and you can answer them in due course of time. Thank you very much, Professor. I think, okay, I shall close this session, Dr. Nanda.
Okay.
Yeah, thank you very much.
Thanks a lot, sir, for your valuable presence, Professor Akira. We are really blessed with your presence. Thank you very much.
Thank you.
Yeah. Okay.
Thank you, Professor Rane, for carrying out such an enlightening session with Professor Akira. I am particularly...
My friend, Professor Rane, Principal Vrinda Bolkar, my friends N.B. Singh Sahab, KPS Sharma, N.N. Ghosh, Sagar Mitra, Louis Figueiredo, Nirmalya Vallabh, Sunji Bandrov, and all the participants. After listening to such an enlightening talk by Professor Akira, I think it would be wise to link the two topics. The symposium topic is on material science, and Professor Akira, one of the questions was on the heat dissipation. What are the security features of against fire and other things, superheating of the lithium battery? So I shall be discussing something about the heat analysis or thermal analysis and its role in optimizing the temperature of sintering or producing ferrite nanoparticles. I would request, because the PPT is I am unable to upload here, I would request to upload it from there. Dr. Fernandez, please. We are living in an era of nanotechnology, and discussion of nano-size materials is incomplete without discussing ferrite nanomaterials. Ferrite nanomaterials are one of the wonder materials having variety of applications. They are wonderful, they are interesting, optical properties, magnetic properties, electrical properties, have resulted in revolutionizing technologies involving production of or manufacture of storage devices, data storage devices, sensors, and many such things. And the preparation of ferrite nanomaterials, like preparation of any materials, depend upon the way they are prepared, they are synthesized. And the method of preparation determine the size of the particle, the properties of the particle, and the properties determine the applications. Coming to materials, materials have many forms. There can be bulk materials, we know coatings, we know fibers, we know fabrics. There can be active materials, they can have passive functionality. And the concept of design in functionality is there. It has become very significant today. Design, what sort of properties we desire in a material that we are going to prepare. So how to bring those properties
by altering the method of preparation so that it reacts in a desired way under any stimulus. The materials are classified in many ways. There can be composite materials, hybrids, interpenetrating network on the structure point of view, coatings, interfacial biomimetics, which is very close to behavior of biomaterials, nanostructure materials, structural integration, materials modeling. These are very important things today. Coming back to multifunctional materials, because ferrites are multifunctional materials, it is one of the best multifunctional materials that we use today. Let us see what multifunctional materials mean. Multifunctional materials have ability to react upon an external stimulus, has ability to respond to their environment in a useful manner. So they are technologically significant. By standardizing their behavior under external stimulus, we can measure their behavior, we can observe their behavior, we can monitor their behavior, and then we can know what stimulus they have been put to. So they can easily be used as sensor. They are smart. They make smart systems, and through using them, smart systems are being developed in which they have a they have very interesting properties, and because of the interesting optical properties, electrical properties, mechanical characteristics, they are very stable, and they are corrosion resistance also. They are hard. Many ferrite materials are very hard. So and besides these, they respond to external stimulus in a standard way, simulating the behavior of nature's materials. And in this category, ferrites fit best. Nanomaterials show different properties, and their properties determine their applications. What is the dispersibility in a suspension? What is the dispersibility of the nanoparticles? What is the compactability in consolidation? If it is hard, what is the compactability? What are the colors in case of metal and semiconductor quantum dots? What are the compatibility in case of nanocomposites? What are specific electrical magnetic properties for data storage, for sensors? What are the photoluminescence properties for certain optical devices? At what in what range, in optical range, they absorb radiation, whether they can be used as microwave absorbers, and so on and so forth. So taking all these things, let me remind that there has been exponential growth in the applications of commercial electronics following discovery of certain very useful inorganic materials. Among them, ferrites are the most important because of their electrical properties, because of their standard magnetic properties, their optical properties. They are very exciting. And you must have noticed, I think everyone is aware today of the transformations, of the revolutions that we have been passing through in data storage. Just see, till few decades back, we could not think about data storage of more than 20 GB without hard disk in computer. But today, we are able to store data in terabytes in very, very small chips today. And the quest for magnetic nanoparticles that could be used for high density magnetic recording, for sensors, etc., attracted workers towards ferrites. I shall be talking about 4 ferrites that we have worked: the cobalt ferrites, barium ferrites, samarium ferrites, that rare earth ferrites, because rare earths are known for their interesting magnetic properties. They are magnetic garnet, iron oxide magnetic materials having general formula of Re3 Fe5 O12, where R is the rare earth iron. It has I'm talking about samarium ferrite. It has high resistivity, it has low dielectric loss, it has narrow ferromagnetic resonance line within microwave region, so it has very low microwave loss. Then magnesium ferrite. The properties of these materials, the ferrites, depend upon the way these ferrites are prepared. The method of preparation determines their particle size, and the method and the method of preparation. So what we have done in these 4 cases, we prepared citrate precursor and then annealed it. In some cases, sintering was also done, heating it for certain period, 3 hours or like that, at a particular temperature, 600 or like that, 500, and then suddenly cooling it down to ice temperature, heat quenching. So annealing, sintering, and heat quenching. So what is happening upon different heat treatments, annealing or sintering, annealing, sintering, or heat quenching, what is happening, and what impact of the period of heating does have on the property of the particle, the size of the particle is very important. So these are standardized using citrate precursor method, and citrate precursor method is very effective in getting homogeneous. So homogenization is very convenient here, and at relatively low temperature, the nanoparticles could be prepared. And for understanding, for optimizing the temperature, and for determining up to what temperature the heating of the gel or the fluffy mass that has been prepared, the citrate precursor that has been prepared, up to what temperature it should be heated, the differential scanning calorimetry is used. Differential scanning calorimetry to get the optimum temperature of curing. So at what temperature is it? Differential scanning calorimetry is actually a method in the group of thermal analysis. Thermal analysis is a class of, is a group of techniques in which the temperature, which is a temperature, and it is a property which is temperature dependent, is monitored with respect to temperature. So it depends upon the property that we monitor with respect to temperature. The method is known. Thermogravimetry, in which the graph is in thermogravity we monitor mass or weight loss with respect to temperature. In differential scanning calorimetry, the property is enthalpy or heat flow. In differential thermoanalysis, then TMA, DMA, differential mechanical analysis, and so on forth. Coming to differential scanning calorimetry, about which I was talking, it is a typical differential scanning calorimetric curve is shown here. It is temperature versus heat flow. It is temperature at heat flow. The temperature is increasing this way, and heat flow, it is exothermic and then endothermic. So this is the zero line, you can say. So this is the baseline. So this way, if the baseline shift, it is the glass transition point is indicated. Glass transition means if you have hard butter kept in deep freezer, if you bring it out, it is hard. Then at what temperature it becomes soft, the glass transition point it determines this. Then this peak indicates it may indicate crystallization or polymorphic conversion. Polymorphy in many materials it is there, in substances. And then if a melting comes this way, maybe polymorphic conversion or denaturation, and then cross-linking is there here, and cross-linking, curing, and then this bad shape curve, it shows oxidation and decomposition. So if you heat the fluffy mass, the citrate precursor, you heat it to certain temperature, and then find out up to what temperature we can heat, and see that the process of oxidation or curing is complete. Just for sake of understanding, let us see that differential scanning calorimetry can detect some of the phenomena which are integral parts of our lives, or in any preparation or processing, in any applications. Just see, today we depend on crystallization, we encounter crystallization, we encounter polymeric conversion, we encounter curing, we encounter decomposition, oxidative or otherwise, we encounter annealing, we have been using annealing here, we encounter phase changes, solid, liquid, gas, or glass. These all appear in differential scanning calorimetry. For example, just see denaturation in an interesting peak that will be, see for example protein. Protein foldage will look like this way, and at 90 degree, for example, it becomes unfolded and the peak will come like this. So decomposition, annealing, phase changes, all these are indicated in differential scanning calorimetry. And then just see, this is the specific heat. In a specific heat, temperature curve will come like this. So we can, from differential scanning calorimetry, we can find out the specific CP. CP comes from that instrument, the same instrument, and then temperature. So this peak. And the peak analysis is very important. What is the maximum temperature, Tm, and what is the area under curve, the enthalpy change is indicated. So these are some of the techniques that are used for understanding a process, how far and how this has happened, curing and oxidation and other things. So optimization of heat treatment condition to get nanoparticles is very important, and for that thermoanalysis is used. The important properties that are found, for example, in cobalt ferrite prepared by cited precursor method, cobalt ferrite of significant saturation, magnetization, magnetocrystallization, anisotropy, coercivity, and retentivity values were obtained. And similarly, barium hexaferrite, which is otherwise very hard and very difficult to prepare, could be prepared by cited precursor method in a convenient way at low temperature and very interesting nanoparticles having significant magnetic and photoluminescence properties. And by the properties, different properties, nanoparticles of different properties are prepared by varying annealing time. If we go for annealing for 3 hours, different particles they have different properties, 5 hours, and then 3 hours heating followed by heat quenching, as I was telling. So different properties of the nanoparticles are there, and they can be used depending on the properties that we have. So after synthesizing the particles, preparing the cited precursor, heating it, annealing it, or if we go for quenching it, and then going for its electrical property, studying its electrical property, magnetic property, optical property, go for its structure analysis, electron microscopy, same time, before that XRD, ritual, and other cellular analysis. So we after these studies, we can get the best particles, and we can put those particles for use for technology. Magnesium ferrites have been prepared in monophagic with no detectable impurities. A small crystalline size of 13-14 nanometer at low annealing temperature it could be prepared. 460. So they show super paramagnetic behavior. Samarium ferrites, as I was telling just now, having wonderful optical and temperature dependent magnetization property. So this could be prepared by cited precursor method by heating cited precursor up to a particular temperature for certain time, which was standardized, and the temperature was chosen on the basis of the peaks in the differential scanning calorimetry and analysis, understanding the thermal differential scanning calorimetry data. The photoluminescence properties are observed fluorescence spectrometer, magnetic hysteresis loops, and then the VSM and dielectric measurement. All these things are used for understanding the electrical, magnetic, and optical properties. Hexaferrites, just giving emphasis on barium hexaferrite, I am pointing out how it is the cited precursor method is convenient. Hexaferrites are interesting ferrimagnetic materials. They have hexagonal crystal structure. They are among technologically and commercially most exciting materials and substances. They are known for their magnetic anisotropy, which is larger than that of the series of the spinel group. They are hard and have better high frequency magnetic properties. They are being used for microwave electronic components, radar absorbing materials, in variety of materials having magnetoelectric and multiferroic applications. But preparing them is very difficult. They are among uniaxial metal ferrites with high magnetic saturation values and high coercivity values. They have hexagonal structure of magnetoplumbite type. They are alternating hexagonal spinel blocks, bringing similarity in structure with both garnet and spinel ferrites. They have many unique features like low-cost material with high magnetic anisotropy, remarkable corrosion resistivity, which I was talking just now. They have remarkable corrosion resistance. They are stable, so ultimately they are very, very, very cheap. And application as permanent magnet, they are used as permanent magnet. They are used in recording media. They are used for microwave filters. They are used as magneto-optic materials. And fields such as electromagnetic interference, electromagnetic radiation pollution are incomplete without barium hexaferrite. So just like in biotechnology, without Escherichia coli, the study is incomplete. We begin with it. Similarly, in the field of electromagnetic radiation pollution, it is incomplete without barium hexaferrite. And they are wonderful microwave absorbers. But it is very difficult. They are interesting, they are very important, they are very useful, they are very versatile in their applications, but it is very difficult to prepare spinel ferrites. So how to prepare the high temperature, because preparing them requires high temperature and pressure, and reaction takes much time. But at higher temperature, because of the gamma Fe2O3 is disfavored and formation of alpha Fe2O3 takes place. So that is another thing. So in this work, we have used very low temperature because of cited precursor method and heating the synthesized barium hexaferronane using chemical based cited precursor method. So this is this paper. I am just giving a reference. This is our paper in Journal of Thermoanalysis Calorimetry, barium ferrite. And similarly, cobalt ferrite. Cobalt ferrite, prepared in a similar way. It has high electromagnetic performance. It has excellent chemical stability, good mechanical hardness, and wonderful high positive first order crystalline anisotropy constant. So this makes it technologically very important. It has cubic spinel structure cobalt, the cobalt ferrite that is prepared by cited precursor method. It has cubic spinel structure, and then in this structure the cobalt plus 2 and then iron plus 3 occupy tetrahedral and octahedral sites. This occupy tetrahedral, this occupy octahedral sites in face-centered cubic lattice of oxide ion. So these are two examples, or say 4 examples of ferrites, and how they are prepared. They can be synthesized at lower temperature in a convenient way using cited precursor method, and their analysis of the study of their electrical, magnetic, and optical properties can make them put to applications. Thank you very much.
Thank you, Fernandez, for assisting me.
Thank you, sir, for providing insights into the preparation of synthesis of the ferrite nanomaterials. If there are any questions, one can unmute and ask. If there are any questions to Professor. If there are any questions to Professor, please unmute yourself and ask.
Deepa, you can unmute. Deepa, you can ask the question.
Yes, ma'am. Yes, ma'am. Good afternoon, sir. It was a very good presentation. I would like to ask one question, that is, now barium ferrite, as you said, is a hexaferrite. Now, if we dope this barium ferrite with a transition metal, say like nickel, then nickel normally occupies the B site. So it would lower the concentration of ferric ion in the B site. So will that lower the magnetic saturation value and its magnetic properties?
Yeah, that is very much expected. Presently, we are working on the impact of doping, and the dopant is a rare, like samarium and other things. So we are looking at what happens, but it is expected as you are telling.
Okay, thank you, sir.
Thank you, sir.
Thank you, sir. Yeah.
Yeah. The next speaker for today's session. I thank Professor Ranjit Verma for providing the valuable information in the preparation of ferrite nanomaterials. It will be indeed very helpful for the students and researchers for their further research studies. And I also thank Professor for spending his valuable time in sharing his knowledge to with us. Thank you, sir.
Thank you, Dr. Miskil. Thank you.
The next speaker for this session is Professor Shunji Bendo. Professor Shunji Bendo is a professor at Nanomaterial Research Center, Department of Applied Chemistry, Meiji University. He is recipient of doctor thesis from Tokyo University of Technology, Faculty of Science, Advanced Study of Chemistry, Japan. His research thrust in the area physical chemistry, nanocarbon, oxide nanotubes. Is faculty member since 2012 in material science and engineering, electromagnetism, applied chemistry, solid state chemistry, analytical chemistry, etc. He is in committee of fluorescence, and I request Professor Shunji Bendo to present his talk.
Okay, I'm here. This is Bando here. Can you hear me?
Yeah, yes, sir.
Okay. Thank you very much for giving me an opportunity to present my research. And I have two topics present here. And one is they show me my B graph and the effect of nitrogen doping to graphene. The other is the nanowire forming in the nanotube. So the just time just about the 20 minutes. So let's go to the next. Please, next slide, please. From the another furnace. the upside that you can see the melamine furnace. That's the melamine is the molecular form of the melamine that you can see in the slide. And the carbon source is the methane. And when we increase the temperature of the melamine furnace about 200 C, in such a case, melamine vapor generate and they gradually carried by the carrier flow of argon or PR gas. PR gas means including a 10% methane in argon. And get into the synthesis furnace set at about 950 centigrade. And we use the copper foil. Okay, the next slide, please. Next slide, okay. And how to determine the vaporizing temperature of melamine, I explained it here. And the vaporizing melamine, that's the upper graph is just thermogrammetry of the melamine molecules. Just around 200 degrees, the melamine start to vaporize. And just we set around 200 centigrade for the melamine furnace, and the inlet the PR gas for the carrier gas. And the lower column is the sample code, and the top MGR1 is meaning the no supply of the melamine, and the MGR2 and 3 and 4. Maybe 5 there is, but I can't see. But anyway, the increasing the melamine content, the estimated melamine to CH4 ratio is the just right-hand column, just order, the 10 to minus 3 to 10 to minus 1 order. So the increasing the melamine ratio. Okay, next slide, please. Okay, this is a result of the XPS. So the from the XPS spectrum, the center part is XPS spectrum. From the this is the nitrogen 1s level. So from the chemical safety, we can know the what kind of site nitrogen is doped. First, when the melamine ratio is lower, in such a case, that's the red line. The graphic doping of nitrogen occur in the graphic. And when we increase the supplying ratio of melamine, that's the nitrogen source, in such a case, the pyrogenic like doping, pyrogen-like doping is occurred. When you see the left hand side schematic, you can you maybe understand what is the graphic doping and what is the pyrogen-like or pyro-like doping. The pyro and the pyrogen-like doping exist the atomic defect near the nitrogen atoms. And so when we changing the supplying ratio of melamine molecules in such melamine molecules, we maybe control the doping site. Okay, let's go to the next. Next slide, please. Okay, after making the film, we removed from the copper foil. We removed the sample from the copper foil and transferred into the quartz plate and put the 4 terminal in order to measure the electric resistance, temperature dependence of the electric resistance. The result is like this. Okay, the black line is MGR1 is a non-doped sample. That's meaning the no nitrogen doped sample. Resistivity, temperature dependence of the resistivity like this way, almost no temperature dependence between the low temperature of just about 10 Kelvin to 300 Kelvin. when we dope the nitrogen, the graphic type doping, in such a case, just lower, the MgR2 is the graphic type doping. In such a case, the resistivity decreases. On the other hand, when we put the nitrogen, dope the nitrogen like like or like, it's meaning the including the atomic defect. In such a case, the resistivity increased a lot. The MgR4 is like amorphous carbon, a lot of nitrogen in the graphene network, but not uniform. So from this figure, we conclude that the doping of graphic end decreases the seed resistance. Maybe the increase of the resistance is caused by atomic defect, I think. Okay, let's go to the next. Next slide, please. Okay. And this is the simple summary of our experiment. That is the right column to left column. Sorry, the left column to right column. You can see this is the melamine supplying rate against the CH4, the methane. And the doping level of nitrogen just about 1%, 1 atomic percent or small. In such a case, we can control the electric feature of the graphene, but the higher concentration, like a few percent, in such a case, no more electric conductivity appear. This is the simple summary. The seed resistance per square is like this. Please take a look at the right-hand column. That is only in the kilo ohm range. So the result is a low level doping of N, less than 1 atomic percent, effectively modified electric feature. Of course, that is the interesting result, I think. But from this experiment, even obtained above useful information, we encounter the following problem. That's the most serious problem is the reproducibility on the growth of the graphene is rather low. We did a lot of experiment and take out this kind of result. So the next step is reproducibility. We increase the reproducibility of the growth. Okay, next slide, please. Next slide, please. So the problem is here. Why? The reason why. We take attention to the condition of the copper foil surface. Normally a lot of publications you can find in the journal. In such a case, normally the copper, single crystalline copper normally uses. So from such kind of research result, the graphene is favorable to grow on the well-defined crystal lines such as 111 or the 100 copper. Take a look at illustration. This illustration is from the following reference. Of course, the single crystalline copper is very expensive, so that we do not use such single crystalline substrate due to cost problem. So the conventional copper foil is of course the cheaper and in wide use. So we analyze the surface condition of the copper foil. Okay, next please. So normally most of the scientists do the annealing and the hydrogen flow. So when we anneal the copper foil and the hydrogen flow, at around 1000 C. The result is like this. After need, well-defined, well-fertilized surface, we can go to, but of course, a lot of domains appears. Improvement of the surface roughness and the polycrystallization curve after annealing. Then the graphene growth was conducted under following conditions, and the result is the next. Okay, next slide, please. Next slide. Okay. So if we anneal the copper foil, in such a case, sometimes the graphene grows well, but sometimes not. The center part is a Raman result, and both sides is scanning electron microscope, same micrograph. So the see more detail using the magnified SEM. The next slide, please. Next, please. Okay. So a little bit magnified. When we take a look at S1, it's the light column at the top. The small lines you can find in S3 is also. S3 is a little bit low, but the small lines we can see. But the left-hand side, left column, S4 and S5, we cannot see such kind of white line. The white line is the graphene, seed of the graphene, I think. So the graphene certainly start to grow at or around atomically rough point on the copper foil. So to make a flat surface is not good for growing the graphene. Maybe this is directly related to the reproducibility of growing the graphene on the copper foil. Okay, next slide, please. Next, please. Okay, so that we try to make the uniformly rough surface. It's a little bit strange word. The uniformly rough surface by blasting the diamond powder on the copper foil. So that we put the diamond powder on the bio and the copper plate and do the sonication, the strong power sonication, high power sonication. The result is you can see. After blasting the ultrasonic blasting, the rough surface we can get, and we take the repair the graphene. The result is next slide, please. Next slide. Okay, this is the copper as purchased, and the center is the diamond powder blasted, and the right hand side is also the diamond powder blasted at the small size of diamond powder. Okay, to click to the next animation. Okay, after growing the as grown copper foil like this, and then next click next. Okay, this is Raman result. Almost no graphene we can see. Okay, next click. The rough surface is changed to the a little bit flat surface. This is Raman, and the strong Raman signal, and also the final one. Please click to the next animation. Okay. Okay, appeared. All right. So when we make a rough surface, we can get graphene, and the reproducibility becomes high. So in next, okay, next, and this is the transmission electron microscopy. So after removing the graphene from the copper foil, we take a look at the high resolution transmission electron microscopy. In such a case, we can see a small domain size of the graphene grown on the copper foil. So you can see the bottom schematic, the growth of the polycrystalline graphene seed. We can get from the uniformly rough surfaced copper foil, and reproducibility becomes so high. Okay, this is the result and of the graphene growth. And the next topics. Okay, okay, let's go to the next topics of the template. Please, the template grading, the nanowire and carbon nanotubes. Okay, next, please. So in order to use the internal space of the carbon nanotube, we need to take off the tube tip like this. And in order to take off the tube tip, we use the heat treatment in dry air. How to determine the combustion? The nanotubes start to burn at the point where 5 memory rings exist. So the starting of the burning is starting temperature of the burning is just around 400 to 600. It depends on the sample to sample. So it is better to check the sample case by case. When you use the CRT mat, in such a case, just around, well, the 420 centigrade, the burning started. The E-dips is a high quality carbon nanotube. In such a case, sometimes 600, but the 600 start to 550. Here the 600 and 650 temperature necessary to remove the tube tip. So I recommend to do the heat treatment before encasing. So the trial for next for the temperature sensitivity, the first we try to the most nanowire inside the nanotube. Usually the molybdenum disulfide, mostly moly sulfide, synthesis is using the MOO3 and sulfur vapor. That concentration gives free energy for most synthesis. MOO3 and the sulfur does not react directly to the go to MOS2, but okay, please just click to the next animation. Please click. Okay, so the MOO3 plus S2, that is the solid, and the S2 is the vapor. They change to the MOO2 solid to SO2 by vapor from the gives energy. And after that, MOO2 solid to S2 vapor gradually change to the MOS. So the low temperature growth and the slow growth of the reaction is necessary to grow the MOS by using MOO3 and S2 and the heating in closed cell. The open type cell reaction does not progress, but in the closed cell, the reaction will start. Okay, next, please. Next slide, please. This is the result of the after reaction. When we increase the temperature to the bottom, this is the X-ray diffraction profiles. The 200 is meaning that react in ample at the 200 centigrade for 1 week. The reaction does not start up to 300. When we increase the temp, return to, please back again. Okay, that's around 300 molybdenum disulfide formation occur. And then when we see there are two reflections at the lower side, when we increase the temperature, in such a case, the reaction starts rapidly, but at low temperature, slowly is progressing. And the interlayer stacking, we can suppress at the low temperature synthesis. Okay, next slide, please. Next slide, please. Okay, this is a transmission electron micrograph of the nanotubes. The empty nanotubes is meaning the nothing inside the nanotube. When we synthesize the sample at the 300 centigrade, you can see some atomic image, the lattice image inside the nanotubes. And it's different from on the sulfur. The next click. Okay, this I skip to the next. Okay, a resolution is this is a high magnification image of the transmission electron microscope. So that we can see this the rectangular circled part. When we magnify this part, you can see the two lines, the black lines inside the nanotube. That the nanotube diameter is 1.5 nanometer. This is the tube diameter. This is the two lines. It corresponds to the interlayer Mori distance. Take a look at the illustration on the left. So this is the side view of two layers of Mori disulfide. This is the summary. Okay, it's okay. Next, please. Next slide, please. This is the summary of my presentation. Low-level supplying the marine vapor in methane gas works for doping of nitrogen and the graphene, grown copper. The blasting of diamond powder is effective to increase the reproducibility, and the low temperature reaction of solid phase MO3 and the vapor phase sulfur works for temperature synthesis of most nanowire inside the nanotube. Okay, this is my brief result of my research. Thank you for your attention. Thank you.
Hello.
Hello.
Is it open for questions and answers?
Yes, sir. You can ask, sir.
How much time is there? One more speaker is there, no? After this? Hello. I'll ask a small one or two questions. Can you hear me?
Yes, sir.
Professor, just tell me, you said that doping site can be controlled. Well, nitrogen doping sites can be controlled, you said. How do you control that one? And what is the method to put the nitrogen in the lattice?
Okay, and the doping site control may be possible, but it's not sure that the reproducibility is a little bit low. But when we supply the nitrogen source,
what is that source?
We supply the decrease the nitrogen source. In such a case, plastic type doping occur.
Okay, but doping, yeah.
Okay.
One more small doubt for me, that the CC distance is increased, you said. Carbon distance is decreased, increased.
Carbon distance.
Yeah.
For the carbon distance increase.
Increase. But it means carbon, the nitrogen is going where exactly?
But carbon distance, but the nitrogen, the doping level of the nitrogen is very low. Normally the carbon distance does not change so much, I think.
Oh, okay.
Slightly increasing, I think, because the nitrogen gives the electron to the graphene pi band. So in such a case, the CC distance should be increased a little bit, but the doping level is low, so that does not affect so much, I think.
Fine. Now one more small question, I didn't catch that one. You use MOS2.
MOS2, okay.
Yeah, what is the main reason for it?
Oh, MOS2.
Yes.
Why is the MOS2 is, of course, it's integrated, and it is interesting. It gives the interesting future and the interesting electric future.
Does it have higher conductivity than MO3?
But when we dope the electrons to the MOS2 side, in such a case, the superconductivity will appear. As you know, the doping of the potassium, it means doping the electron to the MOS2 layer. In such a case, the superconductivity appears. So maybe the electron transfer from the MOS2 inside the nanotube and the how to say that the carbon layer. It modified the MOS to electric feature, I think.
Yeah. Okay, thank you very much.
Thank you very much.
Hello, sir. I have a question.
Okay.
So you have prepared MOS2. So what is the wire that can be drawn? The dimension of the wire.
Drawn mechanism, you mean?
The dimension that what will be the thickness of the wire that can be drawn from this MOS2?
Grown MOS2.
Yeah. Nanowire.
Nanowire inside the nanotube.
Yeah.
So the nanotube diameter is just 1.6 nanometer. So the nanowire should be smaller than like this. And the length is, I don't know the length, but much more analysis is necessary.
Okay, and what is the resistivity of that wire? Resistivity, yeah.
Radius of the nanowire?
No, resistivity of the nanowire.
Resistivity, normally the MOS is insulated. So when we maybe that is some molecules attached in the nanotube and the charge transfer occur. In such a case, the MOS2 electric feature will change and the electric resistance or conductivity changes, I think. Should be or possibly used for some gas sensor or such kind of one.
Okay, thank you, sir. Thank you for your valuable time and for lucid presentation into the preparation or synthesis of this MOS2. And we are very happy to listen to your talk, and it will be helpful to our research student in their ongoing work, or whoever is interested in taking this research. I think it will also help them. Thank you very much, sir, for your valuable time.
Thank you very much. You are welcome.
Thank you, Dr. Mishkil, for the session. A gentle reminder to all the participants, the feedback form link will be posted on the chat at the end of the session. Our next speaker for the day is Dr. Nirmalya Balla. Dr. Nirmala Ballabh is currently Associate Professor of Chemistry at Indian Institute of Science, Education and Research, that is IISER Pune, India, and a visiting scientist at Laboratory for Micro and Nanotechnology at Paul Scherrer Institute, Zurich, Switzerland. He did his MSc in Organic Chemistry and PhD in Physical Chemistry for University of Calcutta. He has worked as a postdoctoral fellow at University of Heidelberg, Germany, and as a senior postdoctoral fellow at Paul Scherrer Institute, Switzerland. His major research interests are interfacial materials chemistry, fundamentals, and applications. I request Dr. Ballabh to present his research work to the participants.
Thank you very much. Could you please upload my audio recorded PowerPoint? I would like to start by thanking the organizers for giving me the opportunity. Today, I'll be talking about graphene-based supercapacitors, challenges and opportunities. I'm heading interface. Our primary objective is to explore new chemistry and physics at solid-solid and solid-liquid interfaces. Here is one example. When two liquids having copper 2 and iron 2 of such kind mix together, no electron transfer happens, and we get a solid having copper 2, Cn, iron 2 coordination link. Interestingly, when we perform the same reaction at solid-liquid interface, we get a thin film having copper 1, Cn, iron 2 coordination link. Electron transfer does happen at confinement. Another example is metal semiconductor solid-solid interface. What we have achieved is thermally driven resistive switching. Just by changing the temperature from 300 Kelvin to 400 Kelvin, a million-fold decrease in the resistance value was observed. This is an interfacial phenomenon. So, interface is indeed interesting. Today, I'll be focusing on graphene-based supercapacitor. The obvious question is why? It is because of our necessity in day-to-day life, individual level and society level. If we want to run this mega show in a sustainable way, we need to provide clean energy, which can be primarily done by well-established battery technology and the emerging supercapacitor technology. Supercapacitors are a good compromise of energy density and power density. Development of such technology mainly depends on availability of natural resource, fabrication facility, recycling policy. To my knowledge, in India, we are pretty good at lead-acid battery, though we need to seriously look at the recycling policy. As for the lithium-ion battery, please buy one lithium-ion battery from Indian market or check your mobile phone battery. It is clearly written made in X, not India. So, indigenous development of next generation energy storing devices is very much essential. Make in India and made in India. We need to handle this huge number. Energy demand is incredible. Indian population. Even if we contribute bigger to such development, it will appear smaller. Let us look what is inside commercial carbon supercapacitor. And Maxwell is a brand in this domain. If you type the word supercapacitor in Google, you are going to see these images. Such an important device is perhaps one of the simplest devices humankind has made. Two important things one can notice: aluminium and carbon. India's natural resource of aluminium is excellent. We export aluminium, but unfortunately, we import aluminium foil used in carbon supercapacitor at higher cost. Even more exciting is the activated carbon, which is typically made from coconut shell. Plenty in coastal regions of India. We export coconut shell and then import activated carbon at higher cost. So high cost of activated carbon and low durability of commercial carbon supercapacitors are alarming issues. Here, graphene is an effective alternative. The question is how to produce graphene-based materials in large quantity. One realistic approach for batch-wise production of say 100 gram or 1 kilogram is top-down approach, whereby we need to perform one oxidation and one reduction reaction. Oxidation of graphite to graphene oxide, that we don't need to invent. It's already being done in 1950s by Hammers and Ofeman, so-called Hammers method. Little bit of modification one can apply. As for the reduction of graphene oxide to reduce graphene oxide, people are using these reagents. So this is chemical reduction of graphene oxide to reduce graphene oxide. Typically, it is the hydrogen which is being mostly used. In such chemical reduction, average capacitance value of RGO is below 100 farad per gram and stability few thousand cycles. Instead of the crowded path of using hydrogen, we walked through a new path and brought the chemistry of transition metal salt into the picture. To start with, we have explored iron 2 chloride. Here are some microscopic images of graphene oxide and reduced graphene oxide. You can clearly see that very thin layers of GO and RGO are being produced. This reduction is specifically influencing the basal plane of graphene oxide. So the reduction is happening typically in the basal plane and not preferably on the edges. We have used RGO powder as such and assembled all solid-state supercapacitor. RGO powder as such means no further treatment, heat or chemical. Please remember, any such treatments cost additional energy and we should avoid. Here are the electrochemical performances: cyclic voltammogram, charge discharge cycle, cycling stability. No Faradic peak could be observed in the cyclic voltammogram so as charge discharge cycle. We could go beyond 100,000, 1 lakh charge discharge cycle at such a high current density. And what we have observed, more than 80% retention of the capacitance, which is remarkable. We have fabricated flexible RGO supercapacitors by using current collector coated on plastic. Cyclic voltammograms are almost identical in stretching and bending modes. And in such stretching and bending modes, one can even go beyond 500 cycles. And the capacitance retention was found to be 100%. our RGO material is good for both aqueous and non-aqueous electrolytes. To further boost the energy density value, we have explored organic electrolyte. And here are the electrochemical performances. In short, we could increase the voltage range from 1 to 2.5 in acetonitrile. Capacitance values are significantly increased. What is noticeable is the energy density, which is now 60 watt-hour per kilogram, close to lithium-ion battery. Coming back to the table I started with, now we can see our RGO, which is being used for all solid-state supercapacitor application, is on top. Capacitance value, cycling stability, retention, energy density, and power density. According to an expert, the as-assembled all solid-state supercapacitor showed probably the best energy storage performance among pure RGO-based materials that has been reported so far. The question is why? What is so unique about our RGO material? It is because of novel chemistry. We found that the filtrate after one batch of reaction can be used for the second batch of reduction of GO to RGO. So what is happening? GO is getting converted to RGO. This is the reduction at the cost of oxidation of iron 2 to iron 3. Now iron 3 is a Lewis acid and these are aromatic CH. So in the next step, what is happening is this aromatic CH are getting activated by this Lewis acid, so-called aromatic CH activation, Heck type of reaction, or intramolecular cross dehydrogenative coupling. As a result, these are defects which are getting healed. So this is an optimally healed RGO, and we are getting back iron 3 to iron 2 plus. So it's a slow reaction kinetics, defect heal. So our use of transition metal salt for the reduction of graphene oxide to reduce graphene oxide is a unique chemical reduction. Indeed, chemistry of transition metal is fascinating. As I was mentioning, this is the supercapacitor performance of RGO produced by recycled reducing agent. And if we compare it with the first batch and the second batch, then the values are within plus minus 5 farad per gram, the capacitance value. Even you can keep our RGO material for a long time. We have kept RGO at ambient conditions for more than 1 year and evaluated the supercapacitor performance. And now if we compare this performance with a newly prepared RGO material, again the capacitance values are within plus minus 5 farad per gram. So indeed, our RGO material is a very stable material and a quality material. Moving on from iron salt to copper salt, copper 1 chloride, we could successfully isolate 3D mesoporous RGO, three-dimensional structure, mesoporous structures. And the capacitance value is significantly higher. In the case of iron, it was 170. In the case of copper, it is 230 farad per gram. So, transition metal chemistry is like a golden egg. Now we should not cut the hen. We move ahead and use manganese 2 salt, and again consistently isolated good quality RGO. Now if you look the literature, then you'll be realizing that researchers are using 10 weight % PVH to support gel polymer electrolyte. The question is, how desirable is this? So we thought to vary the weight percentage of this electrolyte and evaluated the supercapacitor performance. This is CV and this is CD. What is apparent is all are pretty stable, the capacitance retention. However, when you looked at the capacitance value, look here 15% and 20%. So the values are almost double. Just by adding few drops of water more into the system, the rest things were identical, we could significantly enhance the capacitance value. It reminds me the story of Coca-Cola. More than 90% is just water. My friend Professor M. Radhakrishnan from IIT Gandhinagar is looking this unusual aspect of water in the supercapacitor performance from the theoretical perspective. All this hard work culminated into PhD work of Mr. Plavan Kumar Jha, currently doing postdoc in South Korea, one Indian patent, and the key publication in this journal in the category of United Nations Sustainable Development Goal 7, affordable and clean energy. After having such exciting result, what we face is this scenario. It is understandable because the path is assuring you 99% failure. But there is 1% success. Here, government's role is very important. Government of India has always been generous in research funding. We now need to deliver. With the help of DST, Government of India, ISAR Pune and SPEL Pune, Indian manufacturer of supercapacitor, is joining hands for a mission, affordable, high-performance supercapacitors. As you can see in the DST highlight, ISAR SPL Pune jointly developed indigenous graphene supercapacitors. Prototypes of graphene supercapacitors were already demonstrated in Indian Science Congress 2020 in Bengaluru early this year. Now we are planning to install 30-liter reactor vessels for producing 1 kilogram of RGO at ISAR Pune, followed by fabrication of graphene-based supercapacitors of this specification at SPL Pune. We are also targeting 1000 farad graphene supercapacitor for electric mobility. So what are the challenges and opportunities? So there are a lot of challenges and opportunities for graphene-based supercapacitors. In all solid-state supercapacitors, there are many solid interfaces. Say 1, 2, 3, 4, 5. Each of these interfaces can be certainly explored for further improvements. Specifically, the Fermi level alignment across interfaces is really challenging. Device parts serving for carbon supercapacitor may not serve at all for graphene supercapacitors. This is like phone, old phone, smartphone, 1G, 2G, 3G, 4G and 5G. In fact, industry news tells that graphene supercapacitor of 1000 farad is already being demonstrated. We are also observing something astonishing. Our graphene supercapacitors is showing value more than 1 lakh farad. Maybe quantum effects are emerging in such graphene-based energy storing devices. The work I have presented is mainly the PhD work of Plavan. I am thankful to my research collaborator, Dr. Sri Kumar Kurungot from CSIR NCL, Professor Satish Sokule for setting up Center for Energy Science at IISER Pune, all the funding agencies, specifically Technology Mission Division of DST and IISER Pune. I am thankful to Professor Jayant Udgaonkar, our director, Professor Sanjeev Galande, our Dean R&D, Dr. Rajendra Kumar Sharma, MD SPL Pune, for setting up this joint venture. I am very much thankful to my family. Thanks to Professor Borkar and Professor Nathu and the organizers. I am thankful to Google. I have taken some images and some information. Thank you all very much for your kind attention. I'll be happy to answer your question if you have any. Thank you very much.
Thank you, Dr. Ballav, for your insight into your research on graphene-based superconductors. It definitely made in India is an approach we all Indian scientists need to look upon. So if anybody of you all have some questions, please post them in the chat box. Dr. Ballav will definitely be available to answer your queries. So we'll now go to the next speaker, Professor Sagar Mitra. Professor Sagar Mitra is a professor in the Department of Energy Science and Engineering, IIT Bombay. Professor Mitra has received his PhD degree from Indian Institute of Science, Bangalore, India in 2004. After PhD, he joined Professor J.M. Terrasco's lab as a postdoctoral researcher from 2004 to 2006 to learn the lithium-ion battery science and technology. Later joined in semiconductor industry Sweden as a principal electrochemist, and from 2009 joined IIT Bombay as an assistant professor. Professor Mitra is a co-founder of Virya Batteries, a Sign IITB startup company from IIT Bombay, and working on ultra-safe lithium-ion battery cell manufacturing possibilities in India. I request Professor Mitra to share his research work with the participants.
Thank you, everyone. Can you see my slide?
Yes, sir, we are able to see.
Okay, thank you. So today I'll be talking about TMD materials. Mainly I'll be talking about molybdenum sulfide and tellurium, molybdenum telluride for lithium and sodium ion storage, but I'll be mainly talking about the reaction mechanism. So before starting, so these in the morning, Professor already talked about his life on this and how it came. So this is very simply way. The first battery had a problem because of lithium dendrite issue, and lithium dendrite issue was from lithium metal itself. And the two solutions they thought, one is to remove the liquid electrolyte, and then they introduced the polymer instead of liquid to prevent that. But it was observed that polymer also, since there is a lithium dendrite formation is there because of lithium, so polymer also didn't work out. So the second solution was lithium metal can be removed and then put in intercalation material, and that's a history that graphite and lithium cobalt oxide came into the picture, and the battery what you are using right now, it is based on that findings. If I look at this is the mechanism, I will not go because this morning already talked about it, and I know everyone you know what is lithium-ion battery and how lithium storage is. But here I will give you two new concepts. One is concept is anode-free lithium-ion battery. Other concept is million miles batteries. So what is these two concepts? If you look at the lithium-ion battery in a glance, in an atomic level, one side is lithium cobalt oxide, which is well known as cathode. Other side is graphite, which is known as an anode. And when you make a battery, you need to charge the battery to create a more potential difference between these two, so that ion can move faster. So for charging process, what happened? The graphite is not lithiated, so the lithium comes out from this lithium cobalt oxide structure and goes to the graphite. So now the lithium anode-free culture has come. If you think that this graphite is not there, and instead of graphite, we have a current collector, which is copper. And if you start doing the same process, like charging the process, so lithium is coming out from the cathode and depositing on the very thin film formation on the copper surface. So next discharge, the same lithium can go out. So this way, we can actually make this anode free. And it is a one concept right now is going on. Other concept is how the million miles batteries, it came to the news, and even Tesla is trying. What is the million mile concept? So right now, if you look at it, this cathode, whatever we are thinking, we are using not lithium cobalt oxide. It was introduced in the beginning of the history, but now it came to reduce the other composition, which is NMC and ACA. It is nothing but the same, with the same structural features. Only cobalt is replaced by nickel, manganese, even aluminum, so that it is different terminology comes. But instead of most of the cases, these crystals are polycrystallines. Now the million miles battery claim that if I replace this polycrystalline to a single crystals of this NMC, so then I may have a cycle number increase, and that is already they are working on it. And in the small scale, it was found that the cycle number is enhanced drastically, and that's the reason they say is million miles. So there's a true hope that if you have an anode free, you can have a very high energy dense, what we are right now from here to different level, and million miles that your battery can run for let's say 25 years, 30 years timeline. So that's a true proposition. Right now, industry is trying, even all of our world research people are working on it. And where we are right now, the cell level 180 to 200, and transportation sector is looking for around 350 to 500 watt per kg. And cost, if you look at it, this is an size 150. It is a very low grade is 150, but good grade is 200 to 180. But transportation sector is looking for $100 per kilowatt hour, and grid is also looking for, because they are also same type of gridding. And the main problem, it may not be the cost. Another problem, what if you are going to use this battery in electric car? So I have given a simple example of Tesla car, and the Tesla, the best car right now is 2,250 kgs, and the battery pack inside the car is 450 kgs. So that means 24% of weight itself a battery. So that's a big problem. And India may not go with this type of big cars. Maybe we have to look at the small cars. But that discussion I'm not going to get today. Along with this, we have a safety problems. And then if you look at the history, the energy density has increased starting from, let's say, 30 watt per kg. Now lithium is around 250, 200, 220. So the 4 times increase it has done and around 200 years. And right now we are thinking the energy density will be 2.5 times within 2, 3, 4 years, 5 years timeline. And you have to look at it, how the concept and what are the new concept is required, and then how much effort, how much money is required to push this 200 years to a 5 years timeline. So that's another thing people should think about it. So this is one slide I like him. This is my Professor Jayesh Taraskan. I was trained by this professor, and he is well known on this region. So I like his. Yes.
Excuse me, sir. Your slides are not changing.
Slides are not coming.
No. Only the first slide was seen. Okay, now it has come. Yeah.
So now this slide. Okay. So current slide is okay. So from the beginning, you are not seeing the slides.
No, sir.
No, sir.
Because it is not gone in slideshow.
Now?
You are not displaying the slideshow, sir.
No, that is a problem. Okay. So I am the presentation mode. I'm just cancelling it and then put it back in.
I think Professor Mitra cannot get linked to our webinar, and I would request now Professor Rane to start with the students' presentation. However, we are thankful to Professor Mitra for accepting our invitation and being with us for a long time. Thank you, sir, for your kind support, and we will definitely have you again with live presentation of yours in Dhempe College. Thank you very much, Professor Mitra. Now I request Professor Rane to take over the session of students. Thank you.
Hello everyone. Yeah, let us start with our oral presentation. We have 7 people in this session, and we'll have 5 minutes time to present it, and maybe 1 minute we can give it for the 1 or 2 minutes for the question answering. So we can begin with Dr. Misaki. Hello, can you hear me? Hello. Can you hear me?
Yes, sir, we are able to hear you.
Yeah, please go ahead. There is some.
Hello, everyone. My name is Ai Misaki. Today, I am here to talk to you about our study of.
Started.
Hello, everyone. My name is Ai Misaki. Today, I am here to talk to you about our study of single-walled carbon nanotube synthesis by hot-wall CVD using iridium reactor. By the end of this presentation, you will know an iridium catalyst is useful to obtain small diameter single-walled carbon nanotube on a large scale. Let's start with looking at the experimental procedure by hot-wall CVD synthesis for vertically aligned single-walled carbon nanotube. Our goal is to scale up for production. The hot-wall CVD composed of the quartz tube furnace is cost-effective and easy to scale up. Figure 1 shows the details of our hot-wall CVD system. Moving on the next slide, Raman spectra for flow and thermal dependence. Figure 2 shows Raman spectra of the samples grown at 700 to 900 degrees C and an ethanol flow rate of 100 to 500 SCCM for 10 minutes. Single-walled carbon nanotube were grown from an iridium catalyst. At 700 degrees C, an ethanol flow rate of 300 SCCM is optimum. At 800 degrees C, the peaks become strongest at 200 SCCM. Raman spectra for the samples grown at 900 degrees C, maximum peak were observed 500 SCCM. Equation 1 shows the relationship between the single-walled carbon nanotube diameter. Considering this equation, SWCNT diameter becomes larger as the gross temperature increased. Moving on the next slide, figure 3 shows the relationship between the GSI intensity ratio in Raman spectra and ethanol flow rate for SWCNTs grown at 700, 800, and 900 degrees C from iridium catalyst. When the gross temperature was 700 degrees C, the GSI ratio was kept below under 0.1. At 800 degrees C, the GSI ratio increased. It reached its maximum at an ethanol flow rate of 200 SCCM, where the GSI ratio was under 1.1. When the gross temperature was 900 degrees C, the GSI ratio increased drastically for all ethanol flow rates and it reached its maximum at an ethanol flow rate of 500 SCCM. Moving on the next slide, figure 4 shows cross-sectional and plane view same images of single-walled carbon nanotube grown at 700, 800, and 900 degrees C for 10 minutes under the optimal ethanol flow rates for each gross temperature. When the gross temperature was 700 degrees C, SWCNTs were not grown vertically and sparsely observed. on the silicon oxide silicon substrate at 800 degrees C, vertically alignment single hold carbon nanotube were observed, whose thickness was about 60 nanometer. When the gross temperature was 900 degrees C, moving on the next slide, figure 5 shows Raman spectra of SWCNTs grown at 700, 800, and 900 degrees C under the optimum ethanol flow rate for each gross temperature. When the gross temperature was 700 degrees C and 800 degrees C, RBM peaks were observed in similar region. But 900 degrees C shows that RBM peak observed over 250 Kaiser. This shows the diameter increases at 900 degrees C. Conclusions: we grew small diameter vertically alignment single-walled carbon nanotube in the hot wall reactor by ACCVD with an iridium catalyst. Acknowledgement. Thank you.
Yes, it's now one or two quick questions can be asked by anybody.
I'm sorry, I can not your voice slowly. I'm sorry. Small voice. I'm sorry, I can't hear you.
Okay, anybody can ask one or two questions if you want to give them answer. If you are, anybody can ask questions.
Sir, we will put a question in the chat box. That would be
Okay.
better for them rather than asking.
Okay, then it's
and
okay.
you thank her and let us go for the next speaker, sir.
That's better. That's better.
Yeah.
Okay.
Yeah.
Okay. Thank you very much, Misaki, Dr. Misaki, for your nice presentation and apt presentation. And you have taken right time, the stipulated time. We have completed that one. It was quite clear to us also. And thank you very much for it. The next speaker is Dr. S.S. Nair. Dr. S.S. Nair. Hello.
FTIR analysis of silver nanoparticles synthesized using Azadirachta indica leaf extract. Silver nanoparticles were successfully synthesized using neem leaf, that is Azadirachta indica extract at room temperature. Samples were made for both fixed and varying concentration of extract and silver nitrate solution. During synthesis, color of solution changes from yellowish to reddish brown, which indicates the formation of nano-silver particles. FTIR spectroscopy is used to characterize silver nanoparticles. Spectrum of each samples are different. These are the spectrum of samples prepared by varying concentration of plant extract. Sample A1 is prepared using 10 ml AgNO3 solution and 1 ml extract. In the spectrum of A1, band at 3352.28 cm inverse corresponds to OH stretching vibration. Bands at 2980.02 cm inverse and 904.61 cm inverse indicates the presence of aromatic compounds and proteins respectively. Sample A2 is prepared using 2 ml extract. Here, band representing the presence of aromatic compound changed to shorter wavelength region, that is 2920.23 cm inverse. Band at 840.96 cm inverse represent NH bond, which is also moved to shorter wavelength region. Spectrum of sample A3 is similar to A2. Finally, sample A4, which contains 4 ml extract, shows a peak at 3344.87 cm inverse, which represents OH stretching. And now, these are the spectrum of samples prepared by varying the concentration of silver nitrate solution. Here, sample E10 is similar to sample A1. In spectrum of sample E30, that is prepared using 30 ml extract, band at 3670.54 cm inverse represents OH vibration. Band at 891.11 cm inverse represents NH bond. After comparing it with sample E10, we can understand band representing OH stretch moved to higher wavelength region. For sample E40, which is prepared by using 40 ml extract, shows absorption peak at 3666.68 cm inverse, which represents alcohol or phenol, which is also moved towards higher wavelength region. That is, when concentration of extract or silver nitrate solution varies, spectrum also changes. Other observed absorption peaks in the spectrum are mainly attributed to flavonoids and terpenoids present excessively in plant extract. They act as reducing and capping agent, which leads to the stabilization of nanosilver. When the concentration of extract varies, some changes also occur in their spectrum. It may be due to the change in size of the particle. Thank you.
Okay. Well, will you take one or two questions from me, or shall I thank you? Hello?
Yeah, sir. Sir, can I ask one question first? Can I? Harsha sir here.
Please ask. Anyone has to ask question. The chat
Okay,
box
this
is
girl.
okay, but one or two questions should be asked.
Yeah. Hello,
Please.
this girl. Are you listening? Hello. What is this? How you say these nanoparticles are formed here in your presentation? On what basis you say silver nanoparticles? Hello, can you hear me, this girl?
I think she has.
Hello?
Yeah, she's
Yes,
there.
she's there.
Yeah.
I can hear you. Can you ask once more?
You have said your title only says that you have prepared silver nanoparticles, isn't it? So on what basis now, whatever you have discussed is that you have prepared using neem leaf. Extract is varied, then what is formed and all. Which peak signifies that there is silver nanoparticle formation. When we say our nanoparticles are formed, what is the basic for it?
Hello, ma'am. We have recorded the X-ray refraction pattern of the sample, and we have compared with the peak octet, and from that we have reached a final conclusion that the silver nanoparticles were formed there.
The XRD pattern helps us to know the crystallite diameter, not the nano. Okay,
Yeah,
not particle size. Okay.
Yes, size also we have determined. It's a cluster. Actually, it is came around 32.
Okay.
35. That range we obtained. 36 nanometer actually. We are doing the studies. These are the some basic studies we have conducted, and we are going on that, moving to do much more thing in this.
Okay, all the best and all the best. Yeah.
Okay.
Thank you,
very much, Dr. Nair. Thank you very much.
Yes, sir.
Yeah, very nice presentation, and nicely you answered a bit. Okay. So next person, hello. Next person is Miss Kavita.
Thank you, sir. Thank
Kavita
you.
Naik. Is there? Is Kavita Naik?
Yes, I am there.
Please.
Hello, sir.
Yeah, please go ahead.
To one and all, I am Kavita Kadu, PhD student at BITS Pilani Goa campus. Today I would be talking about interaction of core shell hydroxyapatite nanoparticles with proteins. Magnetic nanoparticles have been extensively studied over the decades for various biomedical applications. However, pure magnetic nanoparticles display toxicity issues. Hence, to overcome this drawback, core shell nanoparticles have received increasing demand because of their improved chemical and physical properties over their single component counterpart. For in vivo applications, nanoparticles are exposed to a range of biomolecules, majorly proteins, which form a corona around the nanoparticles, usually termed as nanoparticle protein corona. The interaction between the nanoparticle and the protein may or may not induce conformational changes, which have various biological effects. Although nanoparticles have been used for diagnosis and treatment, a complete understanding of the influence of various NP parameters on the function of the proteins is equally important. The present study involves synthesis and characterization of multifunctional biocompatible core shell hydroxyapatite nanoparticles. These synthesized nanoparticles were then surface functionalized and their interaction with two model proteins were studied. Iron oxide nanoparticles were synthesized using wet chemical method, and hydroxyapatite nanoparticle was synthesized in situ on these iron oxide nanoparticles. The synthesized NPs were then surface functionalized with TLC and CPC. These surface functionalized NPs were then incubated with proteins, that is lysosomal.
What is the problem?
Were viable up to 30 μg per the successful synthesis of core shell nanoparticles, wherein we had a core of 65 nanometer diameter and a shell of 21 nanometer radius. The core shell nanoparticle had a magnetic moment of 60 millieMu magnetization. The cytotoxicity of the synthesized nanoparticles was tested using dose-dependent MTT assay on HeLa cell lines. The figure shows that the cells were viable up to 30 μg per ml of concentrations of nanoparticles, above which the nanoparticles were seen to be toxic. After incubation with proteins, an increase in the hydrodynamic diameter and a change in the zeta potential values was observed, indicating the adsorption of protein on the NP surface, leading to the formation of PNP conjugates. Native proteins exhibit characteristic maximum absorption at 280 nanometers due to the aromatic amino acids. This absorption intensity was seen to increase in both the cases, which is indicative of the protein binding on the NP surface. A decrease in fluorescence intensity was noted for nanoparticles upon interaction with fuel. Similarly, unfunctionalized nanoparticle upon interaction with pepsin decreased the fluorescence intensity, but a major quenching was seen for CPC functionalized NPs upon interaction with pepsin, which suggested conformational changes of proteins. Although a change in fluorescence intensity was seen for nanoparticles upon interaction with fuel, no change in CD spectra was noted. A significant deviation was seen in case of pepsin A. Nanoparticle upon interaction with pepsin A decreased the alpha helix by 12%, whereas CPC functionalized nanoparticles upon interaction changed the alpha helix by 45%, which is an indicative of major conformational changes of the proteins. TLC and CPC have lithium and chloride counter ions available for diffusion into the bound proteins and are expected to induce conformational changes. However, in the present study, such changes were noted only for pepsin A and not for fuel. This could be possibly attributed to the fact that lithium gets immobilized on the negative surface charges of the nanoparticles and are not available for diffusion. The negative charges on the nanoparticles assist the diffusion of chloride ions into the protein, leading to the unfolding of pepsin A. Surface functionalization plays a crucial role in NPP interactions, resulting in changes in the secondary structure of proteins, and hence in-depth understanding of this is very important for development of value-added functional material for specific biomedical applications. These are some of the references used. I would like to thank UGC DAE CSR, the funding agency for the research grants, SAFE, IIT Bombay and Madras for TEM and VSM analysis, and BITS Pilani Goa campus for giving me an opportunity for doing this research. Thank you.
Okay. One or two quick questions can be posed by anybody. Hello. Any questions, please?
Yeah, hello. I don't know how to raise hand online here. Hello, Professor Rane.
Yeah, please.
Nice to see you here. Rameswar Adhikari from Kathmandu speaking.
Yeah, welcome.
I have a very brief question.
Please ask.
The question is, how does this hydroxyapatite crystals the lady has prepared differ from the natural hydroxyapatite crystals? That would be very interesting to know. Thank you.
You are a person of appetite. Hydroxyapatite, okay?
Yeah, hello.
Hello, sir. The hydroxyapatite nanoparticles that we have prepared are using sol gel method, wherein we have just used calcium and phosphate precursors to synthesize the particles. So basically, we don't have additional fluorides and fluorides ions present here.
So are they identical to natural hydroxyapatite crystals?
Yes, this is the hexagonal phase of hydroxyapatite nanoparticles.
Okay, thank you.
Thank you.
Okay.
Thank you and welcome also, sir. Sorry for interrupting, but when I see Professor Adhikari, I felt welcoming him to this thing, our gathering, sir. And we are really thankful for you joining from Nepal. Thank you, sir.
Thank you, madam.
Thank you very much, Adhikar, and thank you very much, Miss Kavita. Nice, and you could answer properly. Okay.
Thank you. Thank you, sir.
Next person is Dr. Manjunath.
Yes, sir.
Yeah. Are you ready?
Yes, sir.
Okay, go ahead.
And I'm going to present today on the topic Raman analysis of the potassium ion silicate glasses. So the plan of the talk will be introduction followed by sample preparation, then Raman analysis, and lastly the conclusion. Hopefully all this finishes in 5 minutes as the time allotted by the organizers of the symposium. So let me begin. The sample under study is a glass material. As you know, they are amorphous in nature, that is, they possess no regular long-range periodic arrangement. However, at a short range, that is, the local structure of each unit is highly ordered. The glass that is presented here for today's talk are the silicate glasses, and the local structure of each silicate is of a tetrahedral nature, with each silicate atom surrounded by 4 oxygen atoms as shown here. With SiO distance of 1.62 angstroms or 0.162 nanometers or an OO distance of 2.64 angstroms and having the tetrahedral angle between SiO-Si of 109.28 degree. The disorder in the silicate glasses is due to the rotation and bending between the connected tetrahedral units in irregular manner throughout the sample. These major defects occur due to the rapid quenching of the samples from high temperature to room temperature. Next up here, we have similar silicon tetrahedra with the different connectivities. I'm going to repeatedly use the terms Q0, 1, 2, 3, and Q4 while discussing the Raman data. And for those of you who don't know what it stands for, let me just give you a very brief insight into it. A completely isolated silica tetrahedra as shown here is known as Q0, and the one here where the corners are shared by the 2 more tetrahedra are known as Q2. So basically the Q values depend on the number of corners shared by the other tetrahedra. I repeat, only the corners shared by the tetrahedra and not any other individual atoms or ions. So higher the Q values, more is the connectivity, and lower the Q value, less is the connectivity between the tetrahedra. That is, these structures are more of an open type. All samples were prepared by method of matte quenching. The one in figure A is a picture of a failed sample due to the choice of wrong composition, and in figure B is of the perfect glass sample. These samples were then scaled up to 15 grams in a platinum crucible and heated up to 1450 degrees Celsius and air quenched within the crucible to obtain the final glass samples. The dark samples are the one with iron and the transparent are one without ions. Here on the right corners are the compositions of the samples presented here in this talk. The samples were tested for glassy nature by XRD. Later, many other studies were also done, but for today, the talk is focused only on the Raman data. These were collected at the MNIT Jaipur using IRIX Corp Japan-made SDR 500 confocal microspectrometer with focal length of 500 millimeters. All the measurements were carried out at room temperature in the range of 100 to 300 inverse centimeter. The data on the left is the raw data and the data on the right is the final processed data. After minor smoothing and spectral connections as employed and suggested by Myson et al. In 1982 article and Colomban et al. In 2006 article. The total spectra, which is known to be made of several randomly distributed individual structural units, were in effect deconvolvulated by technique of multiple Gaussian curves, fitting using the origin software in the signature SI origin, that is 600 inverse centimeter to 1200 inverse centimeter. Here is an individual spectra of each such sample with Gaussian fits. For better understanding, the fractional QN areas were determined and plotted against the percentage area contribution to the Gaussian fits. So what we observe here is that the sample K1, which is without ions, having a large contribution due to Q3 unit, but on introduction of ions, the K2 and the K3 samples show higher numbers of Q2 connectivities, and the K4 sample shows Q3 and Q4 type connectivities. Hence, addition of ions have surprisingly caused the structure of K2 and K3 to be more of an open type. Comparing this to the data of the lithium-based and sodium-based samples, we see that the lithium have open structures with major contributions of Q1 and Q2, and also good contributions of Q2 in the sodium-based samples. Now, the lithium-based glasses are known for fast ion conduction, and also similarly, sodium-based glasses are studied intensively for its conduction property as a replacement to lithium-based glasses. If we compare the open type structures of the lithium and the sodium-based samples to the potassium sample, there seems to be a good scope for K2 and K3 based samples as also a good electrolyte material. Of course, this is subject to the outcome from the conductivity studies to be carried out soon. Hence, in the conclusion, it can be said that there is a scope for these potassium ion silicate glasses to be used as solid electrolyte material on account of more open structures of this glass when iron is added. Further tailoring of the composition may make these possible candidates for viable new solid electrolytes in competition to those of sodium or lithium type electrolytes. So that's it. Before I end, I would like to acknowledge my research guide, Professor Disa, for his contribution in analyzing this Raman data and also for his project funded by UGC DACSR M209 sanctioned in March 2015. I would also like to thank the organizers of the symposium for giving me this opportunity to present my work at the symposium. A very special symposium where the keynote speaker was none other than the Nobel laureate Professor Akira Yoshino, and also the other eminent invited speakers who have presented a high quality scientific work. So with this, let me end my presentation. Thank you.
Okay, Dr. Manjunath, you can take one or two questions. May anybody can ask one or two questions to him.
Hello, Manjunath.
Yeah, yes, ma'am.
Nice presentation. One question here. Why you say now lithium-based glasses are better than the sodium silicates?
Well, as of now, the property, the energy storage property of lithium-based glasses are much more than that of sodium. The reason for it is told as there's a size of lithium. There's a very small in size. Of course, there's a lot of intensive study that is going on with regard to sodium-based glasses, and they are also showing very good results. So, I mean, in the I think gamma phase of sodium silicate glasses are showing very good results in competition to that of lithium.
So in this study which I have used, potassium also shows very similar open structures. So maybe that some further studies on this, especially from structural point of view, we can also have potassium-based silicate classes also, which can be in competition to lithium as well as sodium, and also it will be highly cost efficient.
Okay. So what about conductivity? What you were mentioning little about?
Sorry.
What about the conductivity you were saying about these glasses?
Yeah, I said the potassium silicate glasses could also be competitive to those of lithium and sodium, subject to the studies of the conductivity. We have only studied the structural part of it, where we know that the structures are open, just as similar to that of lithium and that of sodium. So we have not done conductivity studies yet, as of now. So which we are going to do soon. So with the structural property which is open, and the conductivity property, if the conductivity shows very high, then we can say that yes, this actually agrees with each other, and yeah, potassium based iron silicate glasses could be a good electrolyte material.
Okay, good. Thank you.
Good
luck.
Thank you, ma'am. Thank you, ma'am.
Yeah, any more questions? Any more questions? Anyway, Dr. Manjunath, very nicely you have presented and you are very clear in your the oral presentation also. Thank you very much for joining us.
Thank you,
Next,
sir. Thank you.
Yeah, next person is Amit Kumar. And Amit Kumar and Miss Anu. Hello. Yeah.
Hello everyone, I am Amit Kumar with my colleague Ms. Anu from Chaudhry Ranbir Singh University, Jind, Haryana. We are collectively presenting our research work on Juto-felt parameterization and luminescence characterization of D-white doped white light emitting borosilicate glasses for white LEDs. In the present live, as we have clearly seen, why LEDs are so important. LEDs are used in the vehicle headlamp because they produce a highly intense light with homogeneous in nature. Also, LEDs are used in agriculture sector as well as in the medical field due to the properties like highest lifespan, very high energy efficiency, directional lighting and instantaneous illuminations. If we compare our LED sources from the other light sources, the lifespan of LEDs are very high with high color rendering index, and also they are solid in state, which will prevent it from the damage. Also, they will produce instantaneous illumination and does not contain any toxic like mercury. So the LEDs in the market are the phosphor based LEDs. The phosphor based LEDs contains epoxy resin which will deteriorate at high temperature. Now a good alternative for this phosphor is glass. Why glass is good alternative compared to phosphor? Because of the properties that like low production cost, higher transparency, simple manufacturing process and less damage due to heat. Glass basically contains three major parts: glass former, modifier and intermediates. Glass former build the basic structure, modifier modifies its properties, and intermediates act as network former as well as modifier. In our glass, oxyfluoride, lithium zinc borosilicate, lithium and zinc act as network modifier, oxyfluoride reduce phonon energy, and borosilicate is a good glass former with high transparency and low melting point. So we dope this glass with the rare earth ion to enhance its photonic applications. In our experiment, first of all, we will weigh the different compound according to the composition. Then we will crush all the compound until homogeneous mixture is achieved and put in this mixture in crucible and for melt in a furnace. Then we will get desired melt, put it on a brass plate and quench it, and then anneal for some time, and we will get the desired glasses. Now for the characterization of glasses, I would like to invite Miss Anu.
Hello everyone, I am Anu. I am going to present characterization of dysprosium doped borosilicate glasses. Firstly, we see the XRD spectrum, which shows a broad hump that confirms the amorphous nature of the borosilicate glasses. The absorption spectra of dysprosium doped borosilicate glasses at room temperature have been recorded in ultraviolet, visible and NIR regions. By calculating the area under the curve, we obtain the oscillator strength using Joule-Efflet theory. Now to study the luminescence properties of dysprosium doped borosilicate glasses, a suitable excitation wavelength needed. From PLE spectra, we obtain an intense peak at 351 nanometer, and this excitation wavelength will be used to record the emission spectra. In emission spectra, we get two intense peak at 486 and 575 nanometer, and a weak peak at 665 nanometer corresponding to blue, yellow and red emission respectively. The intensities of these emission bands depend upon the concentration of dysprosium ions. The decay profile of various glasses are shown here. By fitting these curves, we obtain the experimental lifetime, and by calculating the ratio of experimental and radiative lifetimes, we observe the quantum efficiency. We can see from here that glass C is highly efficient. Now to measure the effect on color luminescent emissions of these glasses, CIE chromaticity coordinates have been estimated from PL profiles. Among all the prepared glasses, glass C possesses outstanding white illuminance coordinate at 351 nanometer excitation, which is equivalent to standard white illumination level. Now if I conclude my whole research work, I can see that dysprosium doped borosilicate glasses were successfully prepared. PL spectra shows that UV light can excite these borosilicate glasses. A white luminescence is observed at excitation wavelength of 351 nanometer. Glass C have the excellent quantum efficiency, and the color coordinates are very close to standard white illuminants. Hence, our glass is a potential candidate for white LEDs in solid state lighting. Thank you.
Okay, thank you very much. One quick question, because we are running short of time. One quick question anybody can pose.
Hello, sir. I will ask again.
Yeah, please.
Which rare earth ion you said you doped it with your glasses? Hello.
Yes. Can anybody? Anu? Yeah. Yes.
Which is? They are not there, sir. Hello.
Amit Kumar or Miss Anu?
Okay, they are not there, I think.
They must be there. Okay, okay. If nobody is there, we can say thanks to those two presenters. So now we have two more, and we are running short of time also. Miss Manisha.
Hello, sir.
Yeah.
Good afternoon.
Yeah.
Manisha Malsikar, Assistant Professor from Dhempe College of Arts and Science. And I would like to present work on comparative study of degradation of pesticide thiamethoxam in presence of nitrogen-doped zinc oxide and iron ore tailing as photocatalyst. The outline which I would like to discuss are use of pesticide in agriculture, need of degradation of extra pesticide which act as pollutant, use of nitrogen-doped zinc oxide and iron oxide as photocatalyst in presence of visible light for degradation, and effect of pH in degradation. So let's see about pesticides. Pesticides are widely used to protect the crops from pests, weeds, and other plant diseases. It includes insecticides, fungicides, herbicides, etc. Thiamethoxam is a systemic insecticide which paralyzes the muscles of the insects. It kills the sucking and chewing insects. From the structure, it is clearly seen that it has carbon-Cl bond and also the presence of sulfur and NO2. So there is a need for degradation glass without photocatalyst. 3 solutions were kept in sunlight for 4 hours. After every 30 minutes, sample was recorded for absorbance. From the first graph of absorbance versus time shows that in presence of nitrogen-doped zinc oxide photocatalyst shows better degradation rate when compared with in the absence of photocatalyst. Similar trend was observed for iron oxide photocatalyst. Degradation by maintaining neutral pH. Similarly, it was observed that zinc oxide was found to be more effective in degrading the thiomethoxam at neutral pH as compared to degradation carried out using iron ore reject. So from this, it was concluded that nitrogen-doped zinc oxide and iron ore reject showed catalytic degradation of thiomethoxam insecticide. At neutral pH, the efficiency of photocatalytic degradation is enhanced by photocatalysis. Thank you.
Okay. One quick question in America asked. Hello.
Hi, Manisha.
Nice presentation.
Thank you, ma'am.
So what is the band gap of your sample? What you have prepared? Nitrogen, though. Zeleno.
Hello.
Hello, I'm listening. Hello.
Hello, ma'am. Actually, for zinc oxide, it's 3.2 electron volt.
Okay. Thank you.
Yeah, thank you, ma'am.
Thank you very much, Manisha. Next person, last person, Ms.
Thank you,
Jyoti
sir.
Giri. Yeah. Jyoti Giri.
Good afternoon. Yes.
Hello.
Hello, sir.
Yeah. Jyoti?
Yes, sir.
Yeah. Okay, go ahead.
Is my slide visible there?
Now it's so slowly. Yeah.
So, reducing the use of synthetic polymers such as polyethylene, propylene, and replacing them with the biodegradable polymers such as PLA, PBAT, and moreover, their degradation can be more enhanced by using the biofeeders like MCC, NCC, chitosans. By doing this, we go from the non-greener to greener applications. So here we set our objective of the work to extract the microcrystalline cellulose from the agricultural waste with stock, to compound them with the biodegradable polymer, and to study its degradation behavior. In this work, we took the EcoFlex polymer as a matrix, and here the cellulosic material is the microcrystalline cellulose from the wheat stock origin. The isolation of the microcrystalline cellulose from wheat stock is done by a series of the thermochemical mechanical process, and the extracted MCC is compounded by melt mixing method with the polymer matrix PBAT, and different composition of MCC is kept in the composites as shown in the table. These composites were characterized by different characterization tools. The results of the characterization are shown here. The FTIR spectrum of all composites showed the similar spectrum as that of the PBAT, but still there are some CH stretching which is increasing with the increase of the MCC content in the composites, which shows there is some type of the interaction between MCC and polymer. This is further manifested by the FTIR spectrum of the weighted fiber obtained from the composites. The weighted fiber shows the hydrogen bonding between carbonyl group of the polyester and OH group of the cellulose. It is furthermore manifested by the micrographs where the polymer PBAT wraps the weighted MCC. This indicates the compatibility of the polymer with the MCC. The further micrographs of the composite showed the homogeneous dispersion of the MCC in the polymer, indicating the good compatibility of MCC with the polymer. It is the main point which could relate with the degradation studied by the water absorption, and here in this plot we can see the water absorption behavior is increasing with the increase of the MCC in the composites. That is, hydrophilicity increases with the increase of MCC in the composites. Likewise, the contact angle measurement of the composites were observed, where the contact angle value is decreasing with the increase of microcrystalline cellulose in the composites, and at the same time, with the increase of the time of the interaction, the contact angle value is further decreasing, which indicates the hydrophilic nature of the composites with the increase of MCC. The most degradation parameters is observed by the soil composting. Here, the macroscopic observation of the composites showed that the microbial and fungal attacks on the surface, and the degraded samples were analyzed by the SAME and GPC as well. But after 6 months, we were not able to isolate the samples from the soil, so that we do not have the data of the composites after data after 6 months. In this micrograph, we can see that lots of voids are forming at the place of the MCC. With the time spent on the soil, the composites has the polymer degradation, which is adhere with the MCC as well. With that, the void size is also increasing, where the microbial colony growths were also observed. Here, the molecular observation was obtained by the GPC analysis, and here we can see that the distinct degradation of the polymer can be seen here. 48 kD of the polymer decreased to 18 kD on 4 months of composting with 40 weight fraction of MCC. This indicates the this confirms the degradation of the PBAT. So the soil composting behavior showed the degradation phenomena observed into the soil. Work with successful extraction of MCC from with straw to compound with biodegradable polymer PBAT, and found to observe nice degradation susceptibility parameters such as water absorption is increasing, contact angle value is decreasing as with the MCC content, and GPC data also showed the decreasing molecular weight of PBAT with increasing compost period and increasing MCC content. Still few works are remain to observe complete degradation and mechanism involved in it. Saying this, here I conclude my presentation with my sincere acknowledgements to all my co-authors from Germany, financial supporter DFC, my university, and Nepal Polymer Institute. Thank you very much for your kind attention.
Hello, Dr. Harsha.
Sir, now you ask.
You conclude the session. You conclude the session by posing the questions, and then you can give your own views about the all 7 oral presenters.
Conclude, sir.
Yeah, you just first ask 1 or 2 questions.
Yeah, okay. Okay, Ms. Jyoti, nice presentation and very good work. So, which polymer you said you have used for the degradation?
In this work, I used the polybutylene adipate co-terephthalate, commercially known Ecoflex, and shortly we termed it as PBAT.
Okay. So, are you happy with your results? What you are getting work through?
Yes, I am happy and still not satisfied. Further works have to complete.
Okay, okay. Good luck then for your further studies.
Thank you so much.
Thank you very much. Yeah, sir.
Yeah, you just conclude.
So I have to briefly say about all speakers now.
Just in
say,
5 minutes you can just 2-3 minutes you can talk. Then I'll say bye to them. Yeah.
Yes, yeah. So this session, oral presentations, all were very good. Starting with Misaki, then Suthir, Kavita, Manjunath, all were too good. I really appreciate the research work they take and with confidence what they speak. So I think I hand over to Sir to say the final words.
Okay, fine. Thank you. Thank you, Dr. Harsha. Now,